tutti i convenuti a questo convegno, che è un convegno di lancio, diciamo, dei risultati di un progetto di ricerca che è finanziato dalla Regione Campania, che è un progetto, diciamo, molto applicativo e traslazionale e che mira, diciamo, alla costruzione di un nanosensore per la diagnosi precoce dei tumori della testa e del collo. E ovviamente questo potrebbe essere, diciamo, un futuro molto importante per screening di massa praticamente su individui, diciamo, almeno clinicamente sani, ma che siano, diciamo, portatori di neoplasia, per la diagnosi precoce di questa patologia, una patologia molto invalidante, perché la ricettovia radicale ovviamente causa, diciamo, un'invalidità foneatoria e respiratoria, con rischi di infezioni, diciamo, anche a livello polmonare, molto elevata. Per cui ovviamente una diagnosi precoce di questo tipo di patologia è auspicabile. È una patologia in aumento, al momento insomma ancora una patologia rara, però insomma secondo noi, diciamo, l'incremento dell'incidenza di questa patologia nella popolazione sta aumentando sempre di più durante il tempo. Tenete presente che nel 2036 metà della popolazione mondiale sarà affetta da almeno una neoplasia, se non addirittura due. Quindi ovviamente il campo oncologico è un campo in notevole sviluppo. Quindi passerei la parola praticamente al direttore generale dell'Asl di Avellino, con cui noi cercheremo di stabilire dei rapporti sempre più stretti, perché è il nostro, diciamo, obiettivo, l'obiettivo dell'istituto, che ovviamente poi successivamente esporrà anche il direttore scientifico dell'istituto Gianni Capasso, quello di implementare la presenza dell'istituto sul territorio e di stabilire una forte connection con l'azienda, diciamo, sanitaria locale, allo scopo di definire dei percorsi diagnostici innovativi e di essere di ausilio, un po' come è successo nel periodo Covid, per il territorio. Ovviamente passo la parola al direttore generale, il dottor Mario Ferrante, che ci illustrerà quali sono le strategie dell'azienda sanitaria locale nei rapporti con Biogem.
Salve, buongiorno. Diciamo, io faccio un saluto prima al professore Caraglia, al presidente Zecchino che è assente, ma ci siamo visti qualche altro giorno fa, al direttore scientifico, il professore Capasso, che diciamo mi lega già dall'amicizia dall'università da tempo, il direttore amministrativo, il dottore Cambacorta e tutti gli amici e voi che state qui a frequentare, io reputo questo campus di fatto, perché io sto qui sotto la duplice veste. Uno, che sono il direttore dell'Asl, che comprende tutta la provincia di Avellino. Abbiamo due ospedali, uno è un ospedale, lo chiamo di primo livello, spero che diventi avanzato, stiamo lavorando per questo, e poi abbiamo l'ospedale di Sant'Angelo dei Lombardi e poi abbiamo varie strutture territoriali, hospice e altro, e poi ci sono quello che è previsto dal PNRR, quindi non vi sto qui a dire tutte queste cose. Ma ci teneva a dire una cosa che riguarda la Biogem. La Biogem negli anni è diventata una realtà che man mano è andata a strutturarsi. Ha fatto ricerca e ha fatto tante cose di miglioramento. E veramente è una grande realtà. Quindi a me corre l'obbligo, uno, perché sono il direttore dell'Asl, due, perché io vivo ad Ariano Spino, tre, spesso io mi lamento, nemo profeti in patria, ce l'abbiamo, quindi dobbiamo valorizzare. Quindi voglio dire, se la struttura che sta qui, non è che facciamo sempre gli esterofoli, extra regione, extra tutto, sta qui. Allora, visto che c'è, noi la dobbiamo valorizzare. Io già ho detto a Capasso, al professore Caraglia, che spesso ci sentiamo anche per le professioni sanitarie che insistono nella nostra azienda, a prescindere da tutto ciò che voi ci proponete e che noi possiamo aiutare, perché voglio dire, alcune cose ci vogliono anche grandi ospedali, perché per l'attività più diagnostica clinica, alcune cose necessitano ospedali importanti che fanno grossi numeri. Però per quello che noi possiamo, noi collaboreremo a prescindere. significa che voi potete considerare l'Asl che è un vostro partner per tutte le attività che voi andate a mettere in essere, dalla più piccola alla più grande. Abbiamo parlato l'altro giorno dei organoidi e tutto quello che si poteva fare, che per me è veramente stata una cosa bellissima. Per quello che possiamo, noi daremo una mano. È naturale, se noi fossimo un ospedale azienda importante, faremo di più. Però, siccome in questo caso saremmo stati, come vi ho detto, i cugini di campagna, noi faremo i cugini di campagna per alcune cose. Però dove possiamo avere un ruolo più importante, noi ci saremo. Cioè, potete contare su di noi. Poi in questo caso specifico, noi stiamo implementando una serie di attività che sono anche cliniche e anche, diciamo, dal punto di vista di ospedale che va a implementarsi, in cui ci sarà anche la chirurgia tiroidea come subspecialità. Quindi alla fine, in un certo senso, ci agganceremo in seconda battuta. Se abbiamo reclutato gli anestesisti, adesso ne abbiamo 27 a disposizione, prima ne avevamo 0. Naturalmente ho messo mano un po' alla mia fantasia manageriale, abbiamo aumentato il compenso e sono arrivati 27. Oh, si fa quello che si può, si gioca su tutti i fronti. Però abbiamo gli anestesisti adesso, quindi avendo gli anestesisti avvieremo attività chirurgiche che erano quasi ferme. Quindi ci sarà attività chirurgica, implementazione, le subspecialità, perché come dicevo, il nostro ospedale, ve lo dico giusto perché state qui così sapete poi di che trattasi di questo ospedale, è un ospedale di primo livello. Io dico avanzato perché non possiamo dire che sarà un secondo livello, non potrà mai esserlo, perché il secondo livello è Moscati. Però noi se facciamo le cose di primo livello avanzato, io reputo che sono gli uomini che fanno la differenza. Noi possiamo anche appellarci 0 livello, però se ci sono gli uomini sono quelli che fanno la differenza. Quindi se noi attiveremo una serie di subspecialità nell'ambito della chirurgia, quindi la tiroide, l'oculistica, l'otorino, l'urologia, l'otorino, sì, teniamo 2 dirigenti che vogliono... sì, per questo dico, piano piano creeremo le condizioni per fare questa cosa. Quindi per noi il fatto che ci sia la Biogem, io sono orgoglioso e spesso noi abbiamo difficoltà a riconoscere quando c'è una cosa bella, siamo un po' critici. Non lo so perché spesso si crea queste situazioni. Siccome io ho 65 anni, quindi ho superato la fase dell'essere critico, sono diventato un po' più slatentizzato, allora io dico, questa è una struttura che va considerata, non se ne può fare a meno, ed è stupido non pensare che c'è questa bellissima struttura, e ogni volta che vengo io mi innamoro sempre di più. Quindi dopo se posso vengono una grazia, scopo intero. Voglio dire, è una cosa bella, perché noi non lo dobbiamo fare, facciamolo. E allora se noi siamo del posto, abbiamo questa possibilità e non lo facciamo, facciamo un torto a noi stessi, alla cultura e alla parte scientifica. Siccome ho visto che qui voi ci mettete l'anima, e ho visto pure che avete questa grande professionalità, avete tutti questi giovani, no? E poi anche questi, tutti parlano dei giovani, dobbiamo farli fare, tutti, donne ormai saranno il top, tutte loro faranno bene. Però voglio dire, se noi parliamo solo di questo a chiacchiere, però i giovani li dobbiamo proiettare in una realtà in cui poi possono trovare realizzazione. Esatto.
Siamo liberati di livelli.
E quindi i giovani ci vogliono li dobbiamo dare. E poi chiudo perché io credo nei giovani, perché io nel mio lavoro, e poi so anni che faccio questa attività, non è una cosa, sono stato a Caserta, a Benevento, stavo prima da lì, però vi dico una cosa, i giovani, caro professore, io vedo che i giovani di adesso sono animati da un grande impulso di fare, di conoscenza, di eticità, hanno un approccio etico che a noi degli anni 60, 58, 68 non ci vedono proprio. Cioè loro hanno un culto così forte, spinto, di etico-comportamentale, di serietà. Veramente delle volte io vengo a prendere servizio dei giovani che io ci parlo, spiegare il lavoro che volete fare. Ma quando parlano? Sono tutti seri, parlano con molta compostezza. Io ero abituato a quelli dell'età nostra che si faceva comitato per fare una cosa, invece questi li vedo tutti belli, tranquilli, preparati e seri. Allora noi a loro dobbiamo aprire un po' le nostre possibilità e le porte. Per quello che si può, ribadisco, ci sarà l'Asl, il professore Caraglia, c'è un'amicizia che ci lega, quindi Capasso la stessa cosa, tutti i presenti, gamba corta, tutti, il presidente Zecchino, quindi noi ci saremo, potete contare su di noi come struttura per le cose presenti. Se riusciamo a fare anche altre cose per l'università che abbiamo parlato, lo faremo, e quindi metteremo insieme varie cose che aiutano il sistema. Noi saremo lì a darvi una mano, avete dato una mano anche per il Covid, 400.000 lavori, sembrerebbe che siano state fatte, 400, quindi voglio dire, è stato anche presente un momento aperte le porte, un momento in cui non si sapeva che fare, quindi ecco che è importante mantenere le strutture vive sempre pronte. Io vi ringrazio, passo la parola.
Grazie direttore, veramente a me mi porta l'onore e il piacere di dare benvenuto anche a nome del sempre Zecchino, che per gli imprevisti non può esserci, quindi ribadisco la sua, diciamo, presenza attraverso la mia voce, e ribadisco anche l'affetto, la stima che ha nei confronti del nostro direttore, che ha detto delle parole veramente stupende per quanto riguarda in genere, ma per quanto riguarda mi rubo solo qualche secondo. La Costituzione italiana, che è una delle migliori Costituzioni fatte, prevede tra l'altro un diritto, che è il diritto alla salute. Questo è scritto, diritto, anch'io sono medico di campagna, e per me il diritto alla salute parte dalla possibilità di avere un diritto e poi alla natura. E per avere questo diritto oggi c'è la possibilità di utilizzare delle tecnologie avanzate, anzi avanzatissime, che oggi avremo pochi minuti di queste tecnologie, che meritano, accanto a quello che è l'ospedale tradizionale dove si fanno alcune analisi, ci sono alcuni altri enti, altri istituti, altri centri, che si chiamano centri di ricerca, che collaborano per realizzare questo diritto per il comunità, quello di poter avere la salute quindi una diagnosi quanto più precisa possibile. Quindi non c'è all'interno del Servizio Sanitario Nazionale una diatriba, un antagonismo da chi fa prettamente clinica e chi fa prettamente preclinica oppure fa ricerca motivata a per quanto. E Biogem si pone in questo tipo di ottica, di essere un istituto di ricerca che ha come target quella di fare una clinica un po' diversa, cioè quella di fare una clinica avanzata che ha come scopo di trovare degli aggeggi, degli oggetti di medical device che sono in grado di poter fare una diagnosi precoce, che è la condizione sine qua non per poter poi instaurare una terapia. E di questo stiamo parlando. Il direttore generale dell'Asl è una figura importantissima all'interno del Servizio Sanitario Nazionale, perché è quella da cui dipendono i medici di base, da cui dipendono le cosiddette strutture italiane, quelle che sono la fase avanzata, quelle che stanno sul fronte del contatto con il paziente. Credo che oggi abbia fatto un discorso da presidente proprio, in cui dice: guarda, ci deve essere una collaborazione profonda tra quello che sono le vere strutture di cui primo, secondo, terzo livello e quello che è invece l'attività di ricerca che si rivolge soprattutto alle singole. Biogem da sempre, ma in modo particolare anche in questi anni, ha questo tipo di pratica. Si pone, diciamo, in tutte le sedi, istituti di ricerca che deve competere livello regionale, a livello nazionale ed internazionale per fare ricerca avanzatissima, ma non si dimenticherà mai, né si dimentica di quelle che sono le esigenze del territorio su cui insiste. Se questo concetto non è, diciamo, chiaro a molti, è chiarissimo invece al nostro direttore dell'Asl, che dice di Biogem, che ha ormai una storia quasi ventennale e che ha dimostrato di sapere reggere il confronto con tante altre entità al di fuori della provincia, chiede a voce alta, ma sempre nel rispetto dei ruoli, di poter svolgere un ruolo anche all'interno della provincia di Gistone. E avere un direttore generale che ci dice: voi siete i benvenuti, voi siete per me un punto cardine dell'assistenza sanitaria in provincia di Torino e in Campania, credo che siano le parole più belle. Anzi, poi visto l'amicizia che ci lega con Michele Caraglia su Twitter e rispetto all'amicizia che lo lega con il presidente Zecchino, ho detto: signori, per me quello che voi fate, per me avete la posizione a priori, noi diciamo no, noi ci prendiamo le carte, facciamo le cose. E oggi, per esempio, Michele Caraglia, che ha presente un classico esempio di come Biogem può essere sul fronte non della ricerca che interessa il sesso degli altri, la ricerca che si pone al servizio del cittadino, perché con Michele oggi noi sentiremo la scoperta, la possibilità di aver realizzato questi biosensori, che sono anche importanti perché i biosensori dei piccoli particelle loro possono anche trasmettere a distanza addirittura quello che trovo. Quindi fare quello che è una delle medicine che oggi fa telemedicina, noi con questa cosa abbiamo cominciato a realizzare. La telemedicina è una cosa straordinaria, questo deve avere diversi attori, e comincio dai medici di base, poi si passa alla studi di primo, sono diversi grandi ospedali, però certamente non si deve avere. Poi aggiungere.
Perché io quello che ho notato, io lo dico a voi ragazzi, voi avete la fortuna che la struttura realmente fa attività con grande ambizione, perché qui ha collocato e sta collocando scienziati a fare queste attività, cioè non è che sta facendo reclutamenti tanto per tenere aperta una struttura. Cioè io posso dire, Caraglia è mia amica, è scienziato, Capasso è scienziato, l'altro giorno lo studiava a Roma, Ciccarelli, erano tutti scienziati, cioè gente del settore, sono quelli che possono dire a loro. E quindi voglio dire, è anche fa un'attività che si proietta anche in maniera seria, non tanto per fare una cosa, per farla bene, benissimo. Quindi è una grande cosa, io ve lo devo dire. Poi
mi hai rubato la parola perché voglio completare questo. Sì, Biogem recluta persone che si sono fatte altrove, vengono qui per affetto alla terra, per una serie di circostanze, anche perché trovano Biogem, tra l'altra cosa, è bello. Quando voi entrate qui, vi trovate in un'atmosfera, sfido io a trovare, ma non qui in Giovane Campania, ma nel mondo, una struttura in cui la qualità scientifica di quello si sposa con la politica. E questo è bello.
Sì.
Dobbiamo dire che veramente riesce in qualche modo a coniugare l'attività scientifica, ma io voglio aggiungere una cosa. È vero? Sì, certo. Allora, voglio aggiungere un'altra cosa importantissima che adesso voi lo leggerete sui giornali di Calamari. È vero che Biogem è un record, ma crea persone che, insomma, ma anche cresce persone che in qualche modo, grazie a Dio, si stanno fermando. C'è un esempio freschissimo da vedere. C'è stato l'altra settimana scorsa il congresso della società europea di 20.000 persone che sono soci, una delle più grandi società scientifiche, certamente la prima al mondo. Bene, sono stati presentati 2.820 abstract, 2.820 abstract. Una persona di Biogem si è classificato fra i giovani under 40 come primo abstract di qualità scientifica elevata a livello di una società con 20.000 iscritti, 2.800 e questo non è un napoletano, è uno di più, diciamo, non so se c'è, è uno che è nato a Rocca San Felice, eccolo, Giovambattista ha avuto il diploma, è stato Biogem crea anche questi, e questo è Luciano, è un Biogem però, ma certamente nel campo dell'unici si interessa di dialisi prodotta, una cosa che faremo insieme, come sempre mi dice, lui ha scoperto, insieme ovviamente con Francesco De Rosa, ma lui ha scoperto un modo per poter fare dialisi però senza infiammare la membrana prodotta. Questa è una qualcosa che dovremmo brevettare, farà di risonanza mondiale, primo, ripeto, su 2800 sta presentato nella categoria under 40, cioè sotto 40, il primo, c'è scritto su, andate a vedere, è cosa reale. Quindi questo è di Luciano, ce ne sono stati già. Noi abbiamo ragazzi che hanno lavorato per me, stanno adesso, stanno a Cambridge, stanno ad Harvard, tutti provengono da Dio. È un peccato che se ne devono andare, un peccato, sì. Questo è un problema che tu come presidente dell'Asl devi offrire, e poi tu lo puoi, come che è presidente dell'Asl di ospedale, devono cercare di prendere. Cioè noi cresciamo i ragazzi, poi tocca alle forze politiche fare in modo di creare lavoro qualificato, non come i nostri padri che erano qualificati perché sapevano fare degli ottimi orti o facevano delle cose un po', ma noi possiamo fare delle attività scientifiche ad altissimo livello. Ecco per cui Biogem merita rispetto da parte delle autorità sanitarie, politiche, perché noi cresciamo l'intelligenza in campo biomedico. Ti ringrazio per le parole e credo che tu abbia anche altre persone oggi e veramente noi lo classifichiamo come un giudizio è il dottor Marianna è un amico di Detto questo, credo che passerei la parola. Grazie Mario, grazie di nuovo. Passo la parola a Michele per tu scrivere.
Okay, we switch off to the English language now for the scientific part of the meeting, and I want to go on with the first presentation, and I want to call Professor Amalia Luce from the University of Campania Luigi Vanvitelli, and with a presentation in which she will describe us the world of the extracellular vesicles, and with a special focus on especially extracellular vesicles that are expressed in milk, in buffalo and cow milk. And the title of her presentation is Milk-derived extracellular vesicles, overview of the current isolation and characterization methods. Please, Amalia.
Hello, good morning everyone. Thank you for inviting me here. And I am Amalia Luce, a young researcher from University of Campania Luigi Vanvitelli. And today I will give you a brief overview of the current isolation and characterization methods related to extracellular vesicles. In particular, I'm going to focus on milk-derived extracellular vesicles, which is something I started studying recently. So, extracellular vesicles, also known as exosomes or microvesicles, are extracellular nanostructures surrounded by a lipid bilayer membrane. They usually are spherical in shape and they can carry different molecules. So we can define for the extracellular vesicles the cargo, which is composed by functional proteins, lipids, most of them are sphingolipids, and nucleic acids, so DNA, mRNA, but also non-coding RNA. They are very important because we can state the pathophysiological state of the cells just studying these vesicles. Also, we should consider that EP cargo are heterogeneous because extracellular vesicles are released and are released by all kinds of cells into the human body. So we can define a vesicular secretome. Also, they are important because they can mediate the intercellular communication through the release and the delivery of TD cargo. So if you approach the study of extracellular vesicles, you should take into consideration a new young society, which is the International Society of Extracellular Vesicles. It is a young and non-profit international society which was born in 2012, and they founded a journal, which is the Journal of Extracellular Vesicles, which released guidelines to study and to have standard in the field of extracellular vesicles. They organized many meetings. The next one will be in Melbourne, Australia next year, but also they have a YouTube channel, so you can subscribe for free and just follow in the V Club, so where they can they usually discuss about papers published on this journal. So if we consider the extracellular vesicles, they are pretty new in scientific research, and they've been described for the first time in 1940 as something connected or derived from platelets, or just like platelets dust. The first pictures of extracellular vesicles come from a paper published in 1983, and as you can see here, these are pictures obtained by TEM, so electron transmission microscopy, and you can see a multivesicular body, and inside the gold particles, transferring gold particles. But to define, we had to wait other 4 years to have the definition of extracellular vesicles as exosome, and this was done by a publication on JPC. So why we are these fields are gaining interest? Because we can easily isolate extracellular vesicles from all bodily fluids, such as cerebrospinal fluid, saliva, milk, lymph, bile, blood, urine, but also tears or stool. And we can characterize them by using omic science. So we can make a protein profiling of these vesicles, or for example, we can apply a small RNA-seq and characterize the vesicles. This could be useful to use these vesicles as biomarkers. Also, they have a therapeutic potential because we can use these vesicles to delivery, so as a drug delivery system for chemotherapeutic drug, but also for to deliver nucleic acids. Also, they can be used in immunotherapy, and knowing the mechanism of the uptake, also the secretion of extracellular vesicles, we can inhibit this mechanism. This is quite important if we consider the tumor microenvironment and how the tumor cells communicate with the tumor microenvironment. So, like others biomarkers, the circulating EVS have strength limitation. One of the strengths is that they are pretty stable because they are protected by a lipid bilayer membrane, but also there are many limitations related to the isolation to the IV source or related to the purification of these particles. They've been described historically in 3 classes: exosome, macrovesicles, and apoptotic bodies, and they are defined based on the diameter, because the exosome are the smallest one in comparison to macrovesicles, which are bigger, but also they are defined by different pathway they come from. For example, the exosome comes from late endosome, so a late endosome can unfold itself and create this vesicle, and this process can be repeated many times to create multivesicular bodies. Then this multivesicular body can fuse with the membrane and release outside the exosome. Also, another mechanism, whereas to create microvesicles depends on the plasma membrane. So there are some, in this case, this particle come from budding process from the plasma membrane. Obviously, there are different markers to characterize the different particles. Most of them for the exosome are pretty new, the transpanins, which are present on the surface, but also other proteins such as ALIX, TG101. Instead, for the microvesicles, we can use as a marker selectin integrins, and then we have also apoptotic bodies related to apoptosis. So now, recent years, in 2018, it has been released an updated nomenclature related to extracellular vesicles, released by ASEV, and they distinguish the extracellular vesicle based on the physical characteristics. So the dimension, so large extracellular vesicles, middle or small extracellular vesicles, also the density, but also for the presence of surface marker. So we can define a vesicle is positive for CD63, which is a transpanin, or just for the cell condition. So for example, hypoxic EVS. This is quite an expanding field in investigation. If you type extracellular vesicles and cancer therapy or exosome and cancer therapy, you will have many publications released, articles published in recent years. And I found quite interesting this one, this paper, which is related to the study of extracellular vesicle stem cells. And here, as you can see, Italy is at the third position as a country that studies this field. If you approach to this field, you can many data related to high throughput analysis by different databases. So one of these one of the databases is Wikipedia, but there are also exocast. This is important when you approach for the first time to this field. You want to know if, for example, there are already data on extracellular vesicles. So for the functions, they can have different functions. Physiological condition function, for example, most of them are related to the immune system, heart function, brain function, as already mentioned, stem cell function, but also pathological condition related to immune system escape, neurodegenerative disease, heart failure, or liver disease, and also cancer. So usually when we want to characterize extracellular vesicle, we can proceed with the profiling, and I reported here a classical profiling of extracellular vesicles, which is important to detect macroRNAs inside the vesicle. There are many publications where they discovered the macroRNAs as a biomarker, diagnostic or predictive, starting from extracellular vesicles isolated from urine or from plasma or many body fluids. And they are interesting also for the cancer therapy because they represent a naturally derived system, so with a low immunogenicity, poor toxicity, and high stability. So they can be used for the delivery of macroRNAs, but also of anti-macroRNAs. Also, there are some limitations and they are related to the identification of optimal AV source for the clinical translation, the optimization of the purification methods, definition of the techniques suitable for EVS characterization, and also setting up a regulatory framework to testing EVS isotherapeutic in advanced therapy. But even if there are some limitations, there are ongoing clinical trials on extracellular vesicles delivery in cancer therapy. So what is challenging in this field is related to the methods for isolating EVS. There are many technologies that can be used, and here I reported some of them. And as you can see here, we could isolate extracellular vesicles by centrifugation techniques. So ultracentrifugation, density gradient centrifugation, and they are the gold standard in the field of extracellular vesicles. Also, most of the times they are coupled together to reach a good purity of samples. Here, as a limitation, is indicated low purity if you use just ultracentrifugation. If you have a protocol with a coupled ultracentrifugation density gradient centrifugation, you can have a good pure sample of extracellular vesicles, but at the same time it will be time consuming. Then we have a technology based on size-based technique, so ultrafiltration and size exclusion chromatography. Usually they are coupled together also in this time, and the most important between them is the size exclusion chromatography, and it's economical if you don't buy the columns. Otherwise, it's quite expensive. In this case, they are coupled because you can start from different bodily fluids. I didn't mention, but you can start also from media, culture media. So you have to concentrate the media before loading your sample on a column. For this reason, you can use an ultrafiltration system. Obviously, in this case, you should be aware that some of the particles or the extracellular vesicles could be broken by this method. Also, we can have capture-based techniques based on the immune affinity. And even if in this case you can have an high purity, you should be aware already of the markers that you want to find. So you have to start from a selection, unless you can buy a cocktail of antibodies. And in this case, it will be expensive. Also, we can have a microfluidic based techniques. They are new, and in this case the limitations are related to the complicated equipment, and also the fact that you should use usually you should be trained to use this equipment. So I reported here a publication where they compare different techniques. As you can see in the first graph, histogram, you can see ultracentrifugation, optical density gradient, and also the use of two commercial kits, that are based on precipitation with usually PEG, so polyethylene glycol. And even if in this case you can have a good amount of extracellular expressed as a relative protein level with the commercial kit and a lower level of EVS with the density gradient, if you perform a Gaussian blotting to see the markers, specific markers for the EVS, you can see that in the by using the density gradient, you can have an enrichment of your samples with extracellular vesicles, and this is also confirmed by the TM pictures. So they concluded that with the other techniques, such as only ultracentrifugation or the use of commercial kit, you can have also other contaminant factors, such as the soluble proteins. Then another study, which I reported here, compared different techniques, and one of them is the size exclusion chromatography. And they started from plasma in this case, and they evaluated just the size exclusion chromatography or a gradient centrifugation with size exclusion chromatography, or size exclusion chromatography gradient and also ultracentrifugation, because the main point in this paper was to understand how to get a pure EBS sample from starting from plasma, which contains many soluble proteins. So they evaluated by Western blot the level of apoprotein. As you can see here, obviously the best combination was done by ultracentrifugation density gradient and also size exclusion chromatography. So in the end, what is the best method to isolate ABS? It depends. It depends on the starting material, because we can have different starting material. If you think about saliva, it's very viscous. So in that case, you have to apply another bottle or just a dilution of your sample, for example, the volume, because as already mentioned, you can start from a cell culture condition media. So since not all the tumor cells produce many vesicles, you have to start from a high volume. Also, it's important to take into consideration the downstream analysis, the equipment available in your laboratory, or also the budget available for your research, and the scientific question. For example, I want to validate previous results. In that case, I would go for an immune affinity, because I, for example, already performed proteomic analysis. I want to just to understand if I want to validate my results with specific markers. So also you should take into consideration that the chosen protocol does affect the composition of the isolated ABS, and also it's not possible to exclude the presence of other contaminants, such as soluble proteins, lipoproteins, or complex RNA and protein. As already mentioned, you should also consider the guidelines in this field called MISEV, or Minimal Information for Study of Extracellular Vesicles. They've been published first time in 2014, and then an update was being released in 2018. And they provide so a minimal set of biochemical, biophysical, and functional standards that should be used to attribute any specific biological cargo or function to EBS. Also, they created a database of where you can upload and also see all the information related to specific protocol. So they are very specific. So if you, for example, start working with extracellular vesicle and want to have information about the rotor or the ultracentrifuge, you can relate to, want to relate to publication, you can just look for it, obviously, if the researcher used this method. But this is a kind of database created to have a standard in this field. Also in the MISEV, the update version of the MISEV, you can find information related to characterization of EBS, because you have to, after the isolation, the next step is the characterization of EBS. This can be done by Western blot, and that is one of the techniques used, but you have to at least detect 3 proteins, so three markers. One is phase markers. Most of them, as you can see here in the first column, are tetraspanin, or just as a second marker, cytosolic proteins, such as, for example, ALIX or HO proteins. But also a major component, non-EP, that can be co-isolated with the structure, like I already mentioned, the apoprotein. So the next step is the characterization of EDS. Usually this is done by using transmission electron microscopy. This is a work related to milk, and as you can see here, you can see vesicles, or you can use a nano NTA or nanoparticle tracking analysis. In this case, with NTA, you can have an idea of the diameter of your particles, but also the concentration. In this case, the problem related, limitation related to the use of an NTA instrument is that you are not sure about the particles. You don't know if the particles you are going to see, you are seeing, are extracellular vesicles, because it can detect any kind of particles. And also, as a third system usually used is the Western blot, because you can detect specific marker of extracellular vesicles. So usually they are used together, Also, another method which is new is the characterization made by a flow cytometer with the use of immunoaffinity system. So why the milk-derived extracellular vesicles are important? Because they can have different function, and they are the most important thing. They are pretty stable, so they can be resistant to the harsh condition of gastrointestinal tract, and so they can arrive to the intestine. They can have a function for the immunity. So we can think about the breastfeeding that is important, or also a cross communication between the species by having as a food cow milk, but also they have an effect of the metabolism, glucose lipid metabolism, and also on the nervous system. As I mentioned here, also is supporting this table. Also, there are a difference in the expression of the microRNAs or the proteins in milk-derived extracellular vesicles, so just extracellular vesicles, depending on many factors. If you think about breastfeeding, for example, it's important also the maternal nutrition, the maternal disease, maternal lifestyles, and these are some of the factors that can influence the production or the composition of extracellular vesicles. Apart from the immunity, which is the most important function related to the milk-derived extracellular vesicles, there are other functions, and as application, as new application, there is also medical beauty, because they can promote skin regeneration. Here I reported this table, which is important for me, because obviously this was quite a new field for me, and I wanted to understand what was the best isolation procedure for the milk-derived extracellular vesicles, and most of them are ultracentrifugation or density-graded ultracentrifugation. Here it's reported also the limitation and the advantages of all of them. As you can see here, density graded, you can have a pure sample, also with the size exclusion chromatography or affinity purification. So what I've done, I started from buffalo and bovine milk. The main problem related to the milk is the presence of caseins inside my sample. So I had to understand at the beginning if I wanted to remove the caseins or just breaking the caseins by using a chelating agent. I tried to do that, but then in the end I decided to overcome this step for the reason that using chelating agent, I could have modified the proteomic profiling of my extracellular vesicles. So for this reason, I just applied ultracentrifugation. As you can see here, there are many ultracentrifugation steps, and then density gradient. So the second one, it's important because you can remove, it's the fatting step, the fat layer from the milk, and then in the end I could get a pellet. This pellet was very jelly and so difficult to resuspend because of the caseins, which create a sort of matrix with the extracellular vesicles. So for this reason, I then apply also a sucrose and OptiPrep gradient to have pure fractions. So these are represent one of the fraction I collected, which contains extracellular vesicles derived from milk. Then after this step, I had to understand what was the fraction with enrichment of extracellular vesicles. So I did a Western blot and I evaluated specific markers, so tetraspanin, CD63, but also ALIX, which is an internal proteins, so cytoplasmatic proteins, and then I also evaluated the presence of the caseins. And as you can see here, for example, in fraction 10 derived from vesicles from buffalo milk, I could see a good, a high expression of caseins, and also in some of my samples derived from bovine milk. So I evaluated different plots and just pulled the fractions with an enrichment of extracellular vesicles and with an absence of caseins, just to get a pure sample. And then I applied the transmission electron microscopy. As you can see here, I could get a good result, I mean, a good enrichment of particles, and here also a typical, I mean, a vesicles with a typical shape, so from bovine milk, but also from buffalo milk. I did this work in UK, so helped by other postdoc, and now I'm at that stage where I'm just doing profiling of extracellular vesicles, proteomic profiling, but also RNA-seq, so to understand the difference in terms of expression of mRNA in these vesicles. I reported here also an interesting and recent paper published in 2021, which is a paper that I studied a lot also to understand the protocol to apply for my study. And they started from milk, from cow milk, but they started from raw milk, indicated by RM, but also from commercial milk. So many studies are done with commercial milk. So they study, they go to the supermarket, take the milk and just evaluate it. So they started characterizing the extracellular vesicles, and as you can see here, made a gradient to isolate the extracellular vesicles, an electron TM analysis, and then an NTA analysis, but also they evaluated the capacity, the ability of these vesicles to be resistant to harsh condition of the gastrointestinal tract by boiling the samples, or just using acid reagents. And they, as you can see here, for raw milk, ABS, there was an expression of one of the markers, which so we can conclude that they are quite resistant. Then they made models of, so they studied the oral administration of extracellular vesicles derived from cow in vivo models of different kind of cancers. So they made a xenograph with the colon cancer, but also a breast cancer model, in vivo model, and they concluded that there was a decrease of the tumor burden in both cases. So they evaluated more than one cancer. But then they evaluated also the administration of for many days of these oral administration of extracellular vesicles to understand what was if these vesicles were able to decrease the metastatic process. But as you can see here, they injected pancreatic cancer cells and then evaluated the development of liver metastasis. And as you can see here, they got a different result. I mean, they used a low amount of extracellular vesicles, so high amount, which was 25 milligram per kilogram of mouse, for the weight of the mouse, and also the double amount defined as a high, and they got, as I show here, an increase of the metastasis, which was correspondent to the increase of the oral administration of extracellular vesicles. So they concluded that they are quite stable under the disease condition, but also they can reduce the primary burden and accelerate metastasis. Also, they did another experiment here shown where they removed the tumor after creating it, and then they used these the extracellular vesicles, and they got a good result. So there was no deformation of metastasis. Instead, there was a decrease of lung metastasis. So they concluded when then the primary tumor is resected to make the RDBS induce senescence in the metastatic site, thereby reducing the proliferation of cells seated in distant sites. So they proposed the use of extracellular vesicles in a second step, where you have already removed the tumor. Obviously, this is something quite new, and many studies should be done to understand also the stability of microRNAs inside these vesicles. So as a take-home message, I want to just highlight something I found interesting in MISEV guidelines. So the use of extracellular vesicles as best terminology for use in publication, the fact that we should use methods that fit for downstream purpose and report them clearly in this database, then establish the presence of EBs with EB-enriched marker, but also the presence of for negative or depleted marker, and also perform a functional analysis of the non-EBS functions to confirm the function of the EBS specific, the EBS specific function. And also there was an appreciation of the EB heterogeneity, because the macrovesicles are also defined as ectosomes or large now EBS, and it looks like they are also important. And to encourage researchers to study also these EB subtypes in functional studies. So I want to thank you, Lab Caraglia's group and Verdelius group, because I did this part of the study in UK and then to Nottingham Trent University. And thank you for your attention.
Thank you, Amalia. There are some questions from the audience. Yes, from Professor Gianni Capasso, and then Professor Giuseppe De Rosa.
Very, very interesting talk.
Thanks.
Actually, from you can see, you can know that chemistry, extracellular microbiome, that are amount importance for several functions. One of the functions that we have found that it can be used in other ways to transfer information from along the network. In other words, there is a crosstalk between cells from the proximal tubule to the cells of the distal tubule. It's very extremely interesting. Kind of information, a kind of mechanism, because you know that sometimes these longitudinal cells that it goes from the proximal to the distal tubule, then they may function in some way in corroborations, so they can teach the distal tubule cells what they have to do in order how they perform the proximal key. There is any other site in the body where this kind of transformation of information can be transferred by the macrovesicles?
Yeah, for sure, because if you think that all the bodily fluids can be used, for sure we can have this mechanism. I can say that for the urine, for example, there is a task force from the Asl, and what is important is to find the origin of these extracellular vesicles. Because to use them as a biomarker, consider that the urine go through a long path and to understand if they are related to inflammatory disease or if there is, for example, a connection with the diabetic patients. They want to understand what is the origin. So what are the cells where they come from. In my opinion, what I found interesting in terms of communication is the fact that there is also a communication between the species, because if we think that we have food and also in the environment we can have extracellular vesicles, also in cow milk or butter milk that we have, so there is also this cross-contamination. Also, obviously, they are important in blood, and also there is an important thing to take in consideration, which is the plasma or serum. But usually it's used plasma as a source of extracellular vesicles, and inside, obviously, if you think about the blood, there are many biomarkers that can be found.
Thank you, Anna. Very interesting. I think we should consider the possibility to use these vessels also as part of the system, in particular on the topic of isolation, production, and with your knowledge, it's possible to use isolate these vesicles at large scale. So, for example, at liters, in order to feed the pharmaceutical development.
This is an important point, because as you can see, the source is important. So if you think about plasma, you can have a good amount, but at that point there is a problem related to the immunogenicity also, even if it's low. And so, I mean, we are at early stages for the translational of these, the idea of using extracellular vesicles as therapeutic. Also because we should study also the uptake system, which is something we don't know yet. So it's something that should be done, I think. Welcome.
Okay, if there are any other questions, I thank Amalia for the wonderful presentation about the world of extracellular vesicles. And we have to invite the next speaker. Please, Gianni.
And the next speaker is Professor De Stefano, and he will present data about the nanostructure materials for biosensing application. Stefano?
Oh, thank you for the nice presentation. Just a moment in order to upload the presentation. In the meanwhile, I would like to thank the organizers for having invited me to present the work we made together on this kind of application. full start. Okay. So in this presentation, I would like to tell you the story which is behind the design and realization of biosensors. That it is a quite long history, and it starts with materials, so very far from the application. So perhaps for the majority of you, it will be sort of a strange journey into physics and engineering, but and that's what we are, because we are a group of physicists that works in Naples in the Institute of Science, Applied Science and Intelligent System, which has many units in Italy, and we work in Naples in research area of the CNR, the National Council of Research of Italy, and we are a group of physicists that works with biologists, cellular biologists, and medical doctor, far from 20 years, more or less. And the difference, the difficulty of a real multidisciplinary approach is what brings you to such important and futuristic approaching to new system of healthcare, as Professor Capasso said before. But this is the only way to do it, to create something that now is still unknown. We have a classic instrumentation of people doing devices. So we have a clean room, quite a big clean room, the only one in the city of Naples, and we have also a lot of characterization laboratories. We also can use the Eurobioimaging facility, which is a very big facility for imaging of biological system. So coming back to the materials, why using nanomaterials? Simply because when you reduce the size of a material, you get new properties. Materials that not emit, starting to emit light. Materials that are made as a flat surface became very spongy with a huge surface that can be used in your device. So it's not only a technological challenge, but is the search of new properties in the standard material. We started more or less 20 years ago by fabricating optical devices in porous silicon. Silicon is the most abundant materials on the earth, and it's the most used in electronics. And at that time, we were made devices for electronics, for consumer electronics, like your cellular phone. And we started to fabricate porous silicon, and only in search of optical properties of porous silicon. And then we exploited these properties down to several devices, also integrated devices with microfluidics and so on. In the years, a lot of materials. We had a lot of nanostructured materials. Each one can have a specific property that can be used to transduce the molecular interaction between two small or two organisms, small molecules or two organisms. All these materials have been synthesized or used, in some cases are natural organisms like diatoms or diatomites, to build biosensors. A biosensor is a device, is something that you should think not as some exotic instruments in lab, but that you can buy and it must work like every other sensor or clinical instrument that you can imagine. It's a complex instrument because it has a biological element, the one that we call bioprobe, that specifically recognize an analyte, and this is the reason why we use bioprobes, natural or synthetic one, because this kind of specific and selective interaction cannot be replicated by human things. only an antibody can recognize in the human blood a protein among the 800 proteins that are present together. This molecular interaction must be transduced in a signal that you can use as in any other clinical device. In particular, we use optical biosensors because we study light. We are opticians, so we study the properties of light, and light have a lot of parameters that can be measured simultaneously, much more than the electric current. So we use light for our biosensors. The first example I want to tell you is a sensor for the diagnostic of Brugada syndrome, which is related to the sudden death syndrome, that is related to a point mutation in a gene that could be detected in the human body fluids. We choose a PNA in this case as the bioprobe that selectively recognizes the DNA of this gene. And we used a nanostructured matrix made by polysilicon and graphene oxide. Why two nanomaterials instead of one? Because two nanomaterials can be combined in order to get more optical properties. In this case, we get reflectivity spectra and emission from the graphene oxide that can be combined in order to check how the things are going on in search of the DNA of the Brugada syndrome. Of course, to realize some kind of the device require a lot of steps. The first thing is to match the two materials. Then is to characterize the new optical properties. All these formula and graphs simply say that we can combine the two materials. The two materials works together as they work alone, and that we can use all the, for example, chemical groups of graphene oxide to link a protein. The protein is needed to properly see how the material is distributed inside the nanopores of the material. The nanopores are something that you can see by naked eye, and you see with very difficulty by electron microscopy. So you can choose a different technique to characterize your device, like confocal microscopy and optical analysis, and we see where the protein is, how the protein is distributed inside the matrix, and this is the way we can design the device with the PNA that should recognize the DNA of the syndrome, of the Brugada syndrome. This work has been done with Professor Oliviero of the Department of Pharmacy in Naples. And at the end of the story, we can detect without necessity of labeling the DNA target, so a label-free detection with a good sensitivity and limit of detection, and also specificity. Of course, this is very important because you should not have a false positive, because it's a diagnostic of an illness, so it's very important not to have a negative and positive control. So at the end of the story, you do a lot of characterization and functionalization, a lot of physics and chemistry in order to get a device that could be simply interrogated to get a quantitative response, which is the aim of a biosensor. More recently, we are working on nanomaterials made by noble metal, in particular a specific form of nanoparticle golds, which are called the nanomushrooms. We fabricate in our clean room with a very simple process. In 4 steps, we get this nanomushroom on supporting surface that could be glass or silicon or even an hard polymer. And why using nanomushroom of gold? Because they have a specific peak of absorbance, so you have a very simple way to look at this sensor, and you have a resonant peak. It's important to have a resonant peak because you can follow how this peak moves when things around the nanomushrooms changes. So it's very easy use this kind of material to make a sensor. And we characterize the shape on our nanomushrooms, which are smaller, quite smaller. And we found that when you change the environment of the nanomushroom, simply exposing them to a mixture of glycerol and water, the peak shifts and shifts a lot, because the sensitivity is very, very, very high. The peaks shift with this kind of sensitivity, which is more than 300 nanometers per refractive index units, which is a very, very high sensitivity. How to use this kind of structure as a biosensor? It requires a modification of the nanoparticles of gold, and we can functionalize with a specific chemistry the nanomushroom by, in this case, we have demonstrated with a biotin-ceptavidin interaction that it works very well as a biosensor, because we bind the biotin on the nanomushroom, and then the biotin recognizes ceptavidin with a very, very high sensitivity, and we believe that we get a record in this case, because we have a 10 at -24 molar as a limit of detection. Of course, if you don't use the biotin on your nanomushroom, you get no signal. So the biosensor is specific. So this is another kind of device that we have realized in our labs. What is in the future? In the future, the flexible optical biosensor will be, of course, the most interesting field that we foresee, because we can combine the optical properties of detection with the property of the materials. Why flexible is so important? Because you can try to imagine the use of this sensor on the human body. Human body is extremely on, not inside. It's very different. On the human body is very a very strange surface. It's a curved surface. Is a humid. Is hydrophobic. It's difficult to make measurement on the human body and not inside. So wearable devices should be the future for detecting a lot of human parameters like temperature, pH, acid lactic concentration, and everything you can find into sweat, for example. And in the future, the so-called point of care testing devices will be made by flexible material. Silicon is not flexible. It's a very hard and brittle material. If you try to flex a silicon wafer, it's breaking in hundreds of pieces. So you must translate all your application field in polymeric field. Why polymeric field? Because polymer can be is a huge family of materials, can be transparent, so can be used for optical devices, can be casted in a very strange and different form, like the one that will be shown you later as the product of our project as nanofibers, and can be also full of water. In this case, we call it hydrogels. Polymers, very spongy polymers with a lot of water inside. This kind of polymers, of course, can have transducing properties, but we want to use the materials that we are used to. So gold nanoparticles or quantum dots that could give colors or could give emission properties to this flexible material. There are a lot of procedures to make nanoparticles. I just recall the big family, top-down approaches and bottom-up approaches. Top-down, you have very regular particles, but you have a very huge instrumentation that you must use to make very controlled nanoparticle. We normally use a bottom-up approach, which is the synthesis starting from the salt, which gives you less control of the shape and dimension forms, but it's very rapid and costly affordable. So our hydrogel plasmonic nanocomposite are made by an hydrogel, which is a polyethylene glycol diacrylate, and nanoparticles and gold nanoparticles. PEG is a very useful material because by choosing the molecular weight of your polymer, you can choose also the mechanical properties. So large molecular weight means a very flexible hydrogen, and you can fill it with the nanoparticles. In reality, there are a lot of methods to make this kind of nanocomposite flexible devices. You can synthesize the nanoparticle and then put inside the polymer, or you can cast together and form the film with some technique. So it's a very flexible production method. Why using plasmonic nanoparticle? Because plasmonic nanoparticle has this very specific property that you again find a very sharp peaks of resonance in the absorbance. So normal UV spectrometer measurements that you are familiar to, and if you change the environment around the nanoparticle, these peaks could shift or could increase or decrease. So you can use the shift of the peak as a signal of your detection, or you can use the decrease of the intensity. So this is just a scheme of how modify the nanoparticles, and when the nanoparticles are modified, the absorbance spectrum changes. It changes, of course, as a function of the refractive index, and it's important that this property, that's a property of the nanoparticle, could be found again in the nanocomposite material, which means that things must change even in the case that the nanoparticles are made in the polymer. And this is what we have verified with our PEG and gold nanoparticles, that by changing the concentration of nanoparticles and their dimension in the PEG, the color changes. This is another very important thing, that the color changes because you can think to make a sensor that gives you an information, not a quantitative information, but a direct qualitative information, simply changing the color, which is not very accurate from the medical point of view, but could be essential if you want to a very rapid response. For example, an exposure to a toxin. You don't want to know how is the concentration in picograms of the toxin. You want just to know if the toxin is present in the air. So a change of the colors could be very good information to get. In this case, we have studied how the peak of the resonant peak changes when you when you capture biotin inside your nanocomposite, polymeric nanocomposite, and you get a quite good limit of detection, but we go further by characterizing our material in intensity of light terms. The use of an hydrogel is very fun, because an hydrogel can swell or can shrink as a function of the water that is present in their surrounding. So when the polymer swollen, swell, the signal decrease, because you are taking apart the gold nanoparticles out of the beam, so we have a decreasing of your signal. In the opposite case, when it shrinks, the intensity goes up, because you are putting together more gold nanoparticle. And the shrinking and the swelling of the polymers is related to the nature of the molecule. If you have an hydrophobic molecule, like biotin, you have a shrinking of your molecule, because biotin get the water out of the polymer. So you get increasing signal, and you can follow this increasing by looking at the intensity of the light. In opposite case, when you have a hydrophilic molecule like septavidin, you get a swelling of the polymer, and you can measure this decreasing of the signal, and you can get a very low limit of detection, which is at the same level of very complicated mass spectroscopy analysis. It's also specific, and it's also very specific if you don't functionalize your nanoparticles. Things can become, of course, much more complicated, because we can design the polymer in a shape of a microneedle. Microneedle are this kind of structure that we made by a polymeric approach, and can be filled with our nanoparticles. So in this case, you have a microstructure that can penetrate inside the skin and directly analyze what is inside after the stratum corneum, which is the first layer of the derma, and which is the strong barrier that you have on your body. And what we get, that our structure penetrates in a simulate skin made of a gel of agar and a PDMS film on top, and it can sense, by changing the color, it can sense the molecule inside a solution. So as a proof of concept, we get a array of sensing microneedles. So things can be complicated, but also fun by changing the geometry of the structure. The same film can be used also to amplify the fluorescence of a molecule. This is a very important technique, because sometimes you want to see where your target is, so you can use sandwich arrays by using secondary labeled antibody. And the problem is that sometimes the fluorescence is too weak to be detected. But if you have nanoparticle which absorbance match the emission of the fluorophore, the fluorescence signal can be enhanced, strongly enhanced. So another experiment that we made using really the same materials is to detect the fluorescence and enhance the fluorescence by using again gold nanoparticles inside PEGDA, and to get the detection of labeled septavidin, which were enhanced by a factor of 10. So it's a very good amplification factor. And if you made the same experiment that I showed before you with a biotin streptavidin. In this case, streptavidin was labeled. In this case, your limit of detection is very much lower than before, and it reached 0.1 picomolar. So with this example, I want to only introduce you to the world of nanomaterials that are really hundreds in literature, and we strongly believe that future biomedical devices will be based on this kind of materials, which are cheap, which are can be tunable, can be easily reproduced in the labs. This is a very important, another very important point. Reproducible in every lab, not only in one center in the world, which is extremely focused on nanofabrication. Techniques should be replicable in all the laboratory, otherwise they are not useful at all. So in the afternoon, my colleagues will give you other examples of nanomaterials, but in nanomedicine as nanovectors and therapeutic agents. And finally, Sara, which is the Dr. Sara Martino, which is a PhD student that we co-share with Professor Caraglia, will give you the final result of the project, which is a biosensor for the detection of mRNA related to the neck cancer. So I would like to thank all my group, my students. I are a lot of years that I am not still not in labs, so everything I showed you is made by them, Bruno, Valeria, and Pia, which is a colleague, and Ilaria, which are researchers that works with me. And I also thank you for your attention.
Okay, thank you very much, Luca, for the interesting presentation. There are some questions from the audience.
Please.
Okay. Yeah, very, very interesting. And just speaking in the field of biomaterials, this will be what we have presented. This kind of biomaterials, of course, you're speaking about the nanovesicle, very, very small vesicles. It would be the possibility to think about a nanomaterial that can capture electrolytes. I mean, I give you one example. We have a patient, let's say, that for some reason they accumulate potassium, okay? And the potassium is present in the intestine. If we have a nanomaterial that can capture potassium and make potassium inside this nanovesicle, we can use that one as a device in order to reduce the blood potassium. So do you think, okay, can you envisage one nanomaterial, again, what you have presented, in order to capture selectively electrolytes?
Okay, as an ideal answer is yes, everything could be done. As a matter of fact, a lot of work must be done because you said a word which is the most highest word that we face every time we can try to do something inside the body, which is selectively. Selectively is really not cannot be made by things that we fabricate. We must combine natural or a natural derived molecule in order to get the selectivity. Because I can answer that any form of quadruplex could bind an ions inside the molecular cage. So I could bring quadruplex and I can shield the quadruplex, but not structure selectively. Each ions could be counted. So it's very difficult to say yes, we can do everything. It's more or less it could be done, but it takes a lot of effort.
Okay, thank you again, Luca, for your presentation.
Welcome.
Let pass to the next speaker. It is Professor Giuseppe De Rosa from the Department of Pharmacy at the University of Naples. And he will show us a presentation entitled, please. Entitled The Liposomes, Lipid Nanoparticles and Cellular Vesicles, Past, Present, and Future of Nanomedicine. Please, Giuseppe.
Okay, thank you, Michele, for the introduction and also for this kind invitation. Starting from, of course, the past of nanomedicine, we have to start from this guy. This guy is Alak Bangam, a Greek scientist that many years ago, working on the membrane, model of membrane, biological membrane, developed a method to prepare something of artificial that are to study the interaction with the drugs of the membrane. And at the moment we talk, when we describe this kind of structure of liposome that are vesicles that are used for drug delivery. These are vesicles that are formed of phospholipids or other kind of lipids that form structure that we can schematize here. As we see here, a bilayer surrounding a nacreous core or more core, because when we talk about vesicles like liposomes, we have to understand that we have not one kind of nanovector. We have a different kind of nanovector, a family of nanovector with different size and different architecture. So, for example, multilamellar, unilamellar, and so on. And each kind of these structure can be suitable for an application, for example, in drug delivery. Here, for example, you have a summary of all the products that arrived in on the market, so that have been approved. But of course, we have, in the case of liposome, a large arsenal of new product and study that are at the moment in advanced stage of study and or in clinical trials. And so trying to summarize the use of vesicles such as liposome for drug delivery, of course, I say that there are different possibilities to use these vesicles. We can schematize the possible application in four. As you can see here, for example, maybe the less known is the possibility to use these vesicles for the slow release of a drug. For example, here we have some example also on the market. It's possible to use a liposome for the prolonged release of drug and that avoiding the frequency of administration. And this is an example of depot-form liposome technology. And at the moment we have 3 products that are already that received the approval on the market: Deposite, Depodur, and Exapparel. But another kind of use with liposomes is also the increased stability of encapsulated drug. And also here we have a very well established example that is now Danoxome. In this case, we have an anti-cancer agent encapsulated into the vesicles, and actually these particles are able to protect the drug against chemical and enzymatic degradation, but of course with other advantages, for example, in higher accumulation in tumor and also reduced in healthy tissue. But we will go on this topic after. because maybe that this is the aspect more known in the case of nanomedicine, the targeting, because nanomedicine and generally liposome are more known for the targeting that can be a passive targeting of active targeting of tumor and tumor cells. I imagine that everybody in this room well known that a drug diffuse, of course, depending on the characteristic of the drug, diffuse through the endothelial cells of the vessel, distributing into the body. However, if we consider the encapsulation into a carrier, for example, liposomes, we have the impossibility to there is no possibility to cross the endothelial cells, so liposome diffuse only in tissue where there is an alteration of the permeability of the barrier, or for example, where you have fenestrated capillary. And this is the reason for that. By using nanocarrier, we can change the biodistribution of drugs. And more interesting, this can be used in the case of a tumor, because in the case of tumor, we have an effect that is well known as enhanced permeability or retention effect, EPR effect, in which you have an alteration of the permeability of the vessels. And so we have a higher accumulation of the nanocarrier into this tissue, more in this tissue and less in a healthy tissue. And this is known as passive targeting, but it's also possible to functionalize these vesicles by using, for example, specific ligands that can bind receptors that are overexpressed on, for example, cancer cells, in order to have a higher selectivity for these cells and also a higher uptake into the cells. And this is well known as active targeting. But of course, it's not so easy, because when you inject vesicles like liposome into the blood, you have a rapid clearance of this carrier, and in order to avoid the clearance, especially by macrophages, circulating macrophages or Kupffer cell of the liver, you can include on the surface of this nanocarrier PEG, for example, an hydrophilic polymer in general, in order to avoid opsonization process to reduce the capture by macrophages, thus allowing to obtain long circulating nanovectors. So in this case, you have the possibility to have the carrier that is more long circulating and with a higher probability to arrive when there are tissue characterized by enhanced permeability of the vessels. And in this case, it's possible to have, for example, targeting of tumors. Here an image of an old work in our group, in which you can see the image of the surface of vesicles of the liposome. The upper image is without polyethylene glycol on the surface, and the lower is on with the polyethylene glycol on the surface. This is a very well-known image in which you can actually see the accumulation of liposomes. In this case, radio-labeled liposomes have been used, and you can see here, this is a pegylated liposome formulation. You can see here some black points where there are the tumor. You can see here, this is a Kaposi sarcoma, and you can see here in this image the accumulation of the liposome that are in correspondence of this tumor mass. Okay, you can make a comparison between the two legs, and in this case, we have one of the first products that were approved on the market for the delivery of doxorubicin. So these are well-known concepts of to use liposome for drug delivery, for targeting, or especially in the case of tumor. But for example, we are also evaluating now a new possibility, for example, using also liposome for drug repositioning. In particular, this is a project in collaboration with Michele Caraglia that we started with many years ago on a molecules biphosphonate, in particular zoledronic acid, that is an approved drug. We can say an old drug, and is used as anti-resorbage agent for the treatment of bone metastasis or to prevent skeletal-related event in the case of osteoporosis or Paget disease. Actually, if we use this drug on cell, you have a very powerful induction of apoptosis on different cancer cell line. However, if you use this drug in vivo, you have a negligible effect because the drug is accumulated mainly into the bone. So, in order to change the biodistribution of the drug, we use the pegylated liposomes. So, in order to reduce the uptake into the bone and increase the concentration of the drug into the, other tissue, for example, in a tumor. And actually, some detail on the preparation, but I escape these technological details. You can see here the two formulations on which we focus our attention. So pegylated liposome with different amount of PEG on surface and encapsulated in zoledronic acid, and here experiments on cells in which we check the uptake of the liposome into the cells with both formulations. And the more interesting here, the cell viability by using the zoledronic acid alone and zoledronic acid encapsulated into the liposomes. And actually, we found here the first surprise, because we found that also on cell, we found a strong increase of the cytotoxicity of the molecule when encapsulated into the liposomes. But of course, we developed this formulation to go in vivo, and actually, we use this formulation in different kind of animal model. Here an example of a prostate cancer model in which you can see here the growth of the tumor. Here you can see the growth of the tumor when the animal are treated with zoledronic acid in free form at two different concentrations, different doses, and at the same doses you can see, but with the encapsulation into the liposomes, that we observe almost the complete inhibition of tumor growth. Okay, so we are talking about the same active molecule at the same dose, but using with a different formulation. And here bioluminescent cells in which you can also visualize the tumor mass. Here the control, here the animal treated with the zoledronic acid. So you can see that there is a reduction of the tumor mass, but the tumor mass still remains there. And here the effect that we observe by using our formulation encapsulated with zoledronic acid. So another point that we can target with liposomes is also the possibility to cross biological barrier. On this point, for example, I'd like to show you some example. Also in the project with Michele, we developed a particular kind of nanoparticles that we name and we patented as a self-assembly nanoparticles that are prepared by mixing liposome with two different component, calcium phosphate nanoparticle and the drug in solution. So we have this mixing and that forming this kind of nanoparticle with the a vesicular drug, vesicular particles in which we have a core, inorganic core containing also the drug. And here the characteristics, the morphology of these particles that were formed by a two bilayer surrounding an inorganic core containing the drug. But more interestingly, as I say, that we used this approach to overcome biological barrier. Actually, we use this kind of nanoparticles by to study new therapeutic perspective against glioblastoma. Our interest towards glioblastoma was due to the fact that this is a very aggressive primary brain tumor, and despite the treatment with surgery, radiotherapy, and associated to chemotherapy, the prognosis remain very poor. And actually, in this case, we include also a ligand on the surface, transferrin, because transferrin is able to facilitate the crossing of blood-brain barrier. This reach of receptor for transferrin by transcytosis, and moreover, we can also have an higher up into the cell, because also the number of cancer cells are characterized by overexpressing of receptor for transferrin. So here the modification of our protocols to prepare the nanoparticles, and here the characteristics of our nanoparticle that I will show you only the final results in vivo. So here the controls, you can see here in orthotopic model of glioblastoma. And you can see here what we obtained by using the nanoparticles. We obtain in no cases the stabilization of the tumor mass, and this is very important in the case of the tumor for which there is not a real therapy. And moreover, we in significant number of animals, we also find the complete tumor regression. And of course, I'm proud to say that this data have also been used by a company, because this product have been licensed to a company, it's a Italian pharmaceutical company, to obtain the orphan drug designation that have been granted by the EMA, European Medicines Agency, and by Food and Drug Administration. There are some words also on the possibility to deliver RNA by using liposome, but in this case, not only liposome, we have also to discuss about lipid nanoparticles. Actually, RNA offer, after the vaccine, maybe everybody know, a lot of possibility. A lot of possibility for a new treatment against disease, because we can use RNA with different strategy. We have small interfering RNA that can silence specific protein. We can have microRNA, already mentioned today, with possibility to regulate different kind of cellular processes, but also messenger RNA, for example, for vaccination, not only against viral infection, but also against cancer, and also for replacement therapies. But the development of RNA-based therapy is hampered by different drawbacks that we can summarize in a rapid degradation into the blood and in general in biological fluids, and also poor uptake into the cells if you directly inject in the action site the RNA. Actually, we can check into the literature. We can find a lot of publication on the RNA delivery with non-viral vectors, and in particular now different nanovectors have been described. You can see here some example. So we have a very huge choice of different architecture in terms of nanotechnology. However, we have to say that after many years of studies, only one kind of technology arrived on the market that we name today lipid nanoparticles. Lipid nanoparticles that start from agent that maybe some of you use into the lab, for example, lipofectamine, lipofectin, that are liposomes characterized by a cationic charge. And actually, these kind of liposome were developed by this guy that I met 1 year ago in Vancouver, Feldner. He developed this kind of protocol that he named as a lipofaction, in which, of course, we investigate, we discovered, we have to say, that cationic lipids forming liposome can bind RNA or DNA, and actually these are uptaken by cells very rapidly by endocytosis. And more interesting, there are some mechanism to release the RNA or DNA into the cytoplasm by different mechanism. Here is schematically reported is the mechanism that is named flip-flop that have been discovered by Zoka in this image. But of course, during the time, this mechanism has been also made more powerful with the fusogenic lipid and so on. However, these kind of product, lipofectin, are only used on cells because in presence of other components, for example, protein, for example, albumin, you can observe a very strong increase of the size. And this can be not maybe a problem in vitro, but certainly in vivo, because in vivo you have in biodistribution that sometimes you need to inject by intravenous administration, and in this case you can see there is a rapid drop of the concentration of the nucleic acid and lipoplexes in general that accumulate firstly into the lungs and then in the second part into the liver. So it's difficult to use lipoplexes for therapy that are outside, for example, of the liver and also on the lung. But this problem have been addressed by Peter Kallis that developed lipid nanoparticles. Actually, the strategy was the modification of the structure because this instability in serum is due to the presence of cationic charge on the surface of these nanoparticles. However, if we use nanoparticles with lipid that are not cationic but ionizable lipid, it's possible after preparation to neutralize the surface, obtaining neutral particles that are stable in vivo. And here a schematic representation of this nanoparticle with all the components. Actually, in literature, you can find this nanoparticle called with different name during the evolution. So SALP, SNALP, and now you can see, to simplify the story, lipid nanoparticles. Everybody name lipid nanoparticles, this kind of nanomedicine, we can say. Actually, why these nanoparticles are not more named as liposomes? Because actually we start with liposome, prepare these nanoparticles, but when you, during the protocol of preparation, there is a step in which you change the pH, and the change of the pH makes the reorganization of the lipids. So, as you can see in this image, here you are vesicles, and when you begin the preparation, but during the preparation there is a reorganization, and you can see that also the aqueous cavity of the liposome is full of lipids. So you have a completely different structure that you can see here compared to the liposome. So this can be considered something different than liposome, but an evolution of the liposomes. So we know very well that with this technology, now it's possible to have RNA-based therapy. For example, everybody absolutely, the approval of the two vaccine, BioNTech and Moderna. Maybe not everybody know that the first product of RNA was approved some years before, was Onpattro, and it consists of a product for the administration of a small interfering RNA by intravenous administration. And but starting from this success experience, now, of course, what is the direction in the field of RNA-based therapy with lipid nanoparticles? Certainly, the majority of companies are now trying to find new lipid, new cationic lipid, because we have to remember that also in the case of the products that are on the market, there are patents only on the specific lipids. So the company are investing on the lipids, new lipids. But I have to say it's very difficult to find new lipids that work properly and that have also the characteristic to fill a patent. Moreover, another effort is also to expand the application, the possibility of application of this technology, because we have only one product for intravenous administration that is able to give liver targeting and also the two vaccine. But we have a huge plethora of possibility that we have to investigate. And moreover, one of the problems is also the stability of these particles, because we remember that it was very difficult to store these nanoparticles we need a very low temperature, okay, for the vaccination. So only to give you some example, here a project that is ongoing together with the Istituto the Regina Elena of Rome, and here we demonstrate the possibility to use these nanoparticles to deliver microRNA against triple negative breast cancer. And so I escape this detail of to give you some details. In this case, we selected the target was the TRF2, that is a part of telomeres, and the majority of the therapy against this kind of tumor is targeting this protein, sorry, this telomere, and it has been found that in higher expression, overexpression of the TRF2 is correlated to resistance to therapy. And so we found that it's possible to use a microRNA 182 to reduce the expression of TRF2, as you can see here. And so we developed a formulation of lipid nanoparticles encapsulating mirs-182, and here there are characteristics of nanoparticles, and here are some experiments on two different xenografts in which you can see that it's possible to reduce the growth of the tumor by using the lipid nanoparticles encapsulating this microRNA. But more interesting, we also found that these nanoparticles were also able to treat the metastasis due to the breast cancer, so brain cancer. Breast cancer brain metastasis, and as you can see here by bioluminescent cells. Okay, this is the group of animal treated with our formulation, and here the control. And only to give you another different example, not in cancer, we also are working on the use of lipid nanoparticle for the delivery of microRNA, for example, to prevent the damage following ischemia, brain ischemia. This is a work in collaboration with Lucia Annunziata and Giuseppe Pignataro of our university, and in particular we are working now on the possibility to restore the function of a channel, a sodium calcium plasma exchanger, this in NCX1, because it has been found that in the case of stroke there is a downregulation of this channel with consequent ischemia into the brain, and in this case we identified a MIR-103 that is able to control the activation of this channel, and actually we use in this case in antagomer to block this microRNA to restore the functionality of this channel. Here, all the detail of these nanoparticles. We prepare lipid nanoparticles with different composition in this case, and also not only lipid composition, but with or without transferrin. I said before that transferrins can be useful to overcome blood-brain barrier. And I go directly to the final results that we have in this moment. So as you can see here in a model of stroke, we found that it was possible to reduce the ischemic area into this model, especially with these two formulations that were the two formulations of lipid nanoparticle targeted with the transferrin on the surface. So a few words on also extracellular vesicles, of course, only for the drug delivery. I have to say that Amalia before me already mentioned very well this possibility. So only some consideration on this topic. Of course, I escaped all the description of these extracellular vesicles. Certainly it's important that these extracellular vesicles as carrier for people that work in the field of delivery, these are particles that can have a high variability because of course we can have a very different kind of lipids. In the case of lipos, in the case of lipid nanoparticles, we can modulate the decomposition in lipids. Here you have a very large variability depending on the source and other factor of the extracellular vesicles. Of course, Amalia already mentioned very well that these are, of course, able to transport active biomolecules from cells to cells, and of course we could exploit this kind of possibility. Well, some lipids are more present inside the extracellular vesicles, for example, and this could be a very important point because in this case we have to know if these lipids are compatible. But I have to say that in the case of extracellular vesicles, a good biocompatibility is also reported because, of course, we are using endogenous lipids. Okay, so mainly one of the point very important is also the low immunotoxicity, because also when we talk of liposomes, lipid nanoparticle, we have to consider, for example, that there are some problems of immunogenicity. For example, liposome, pegylated liposome can also induce a production of pegylated lipids. Sorry, of antibody against PEG, and of course these extracellular vesicles are also efficient to deliver a nucleic acid because this is a physiological role that they have. These are stable for the circulation during circulation, and there are different studies, interesting study that compare also the clearance into the blood compared to liposomes. There are some studies that say that the clearance is also similar or faster to that of liposome, but I consider that we have to well see the specific experimental condition which we use. We make these experiments, so I think we cannot give conclusion on these. Certainly, these are also able to cross biological barrier, and maybe there is also the possibility of targeting because, of course, we have a very complex composition with the protein, with the ligands that can be also used for targeting. So, can we use these vesicles for drug delivery? In my personal opinion, yes, but the ways very far, we can say that the arrival is very far because we have a very, very complex structure with different proteins. So in the case of lipids, in case of liposome, we can prepare, for example, particles with specific lipids, specific protein on the surface. In this case, we have it's difficult to have sample purified, and also maybe a better understanding of the proteomic profile should be needed. Of course, they are able to carry also RNA coding on encoded RNA, so maybe could be also an option to lipid nanoparticles, but at the moment there are this part of the studies at the infancy. And also, in my opinion, there are at the moment a lot of study trying to understand also the exact mechanism that regulate the loading of RNA into these nanoparticles, and also people trying to work on extracellular vesicles for drug delivery have different methods for the loading of these vesicles. And of course, this was already shown that there is a high heterogeneity of the technique to work on these kind of vesicles. And of course, I opened a little bit this morning also the discussion on this point. One of the crucial point is also to work on this technology, trying to upscaling this technology, because if we can see can do something into the lab, sometimes this technique is not transferable at large scale. So we have to select not only the technique that allow for example, the best purification, but also the technique that allow also the technology transfer to have a production at high volume and also in GMP condition. That if we want to think that this could be a strategy that can be used for a new pharmaceutical therapy. And of course, it's possible to sterilize these vesicles, but of course, here we have it's not possible to sterilize as for drugs with heat. But we have to use filtration in this case, and is a method limited for very small vesicles. So trying to make a conclusion on this presentation, I can say that I try to summarize a little bit what we can do as a drug delivery system with a liposome, lipid nanoparticles, and extracellular vesicles. Of course, here, in my opinion, we have the presence of drug delivery, and certainly we have also the future in the case of extracellular vesicles, but also with all the other formulation that we are developing, not only, of course, in our group, but there are on under investigation on the lipid nanoparticle, but also liposomes. Certainly, I'm convinced that we cannot talk of past for this kind of technology, because at the moment I think that there is a regrowth this kind of field, we can say, and at the moment maybe that before pandemic, for example, in Italy, it was very difficult to find company equipped to prepare nanoparticle in general. After the pandemic, the majority of the company are equipped or are equipping the plant for this kind of technology. So I think that this is a good moment also to push on this field. And of course, I present also some of data, but all the data that I presented, and many are that was not possible to present, have been possible thanks to the collaboration with many other different groups. Of course, I have to thank you my research group, but also a big thank you to the group of Michele Caraglia. We have a very historical collaboration. I'm sure that I forgot something, and sorry for this. Of course, thank you to the support that we received by different sources, and thank you for your attention.
Thank you a lot, Giuseppe, for your very nice presentation. There are some questions from the audience. If there are any questions, I want to do one. About extracellular vesicles, do you think that to collect extracellular vesicles will take from the patient and then to upload the cytotoxic drug, this extracellular vesicle, that you re-inject the same extracellular vesicle to the same patient, could allow the distribution of the extracellular vesicle to the tumor sites, because they have some characteristics on the cell membrane that induce a better, some proteins that induce a better distribution of these nanovesicles in the tumor sites. For example, there was additional molecules that are expressed on the cell membrane. What do you think about this?
I think that this is the future, this kind of technology, because at the moment we discuss continuously of personalized medicine. And so we have to think that we have to consider therapy that are tailored on the patient, specific patient. For example, we work with self-assembly nanoparticles. We explain all time during the meetings that this is a way to encapsulate something into the hospital. So before injection. For example, personalized medicine for RNA that are specific for this patient. And in line with these, I'm sure that also the case of extracellular vesicle could be the future in this direction. Of course, I think also that at the moment maybe we are not ready to provide a protocol that could be suitable for this kind of application, but I think that this is the future.
Okay, thank you very much, Giuseppe. And we have now a slight lunch, and we will come back to the room at 2 p.m. Okay, thank you.
So good afternoon, everyone, and welcome to the second session of the meeting on Smart Test project financed by Campania Region. First, I would like to thank Biogem Direction for making possible today, and then I would like to thank the speaker that this morning attended the meeting, excellently discussing about the key role of microvesicles in intercellular communication, the most powerful strategies for their isolation and characterization, and the use of nanostructured compounds for biomedicine. All these topics will be further explored during this session, focusing on the role, the use of nanoparticles, both for drug delivery and for intracellular imaging, and also on the study of the characterization of microvesicles for the identification of novel biomarkers for early diagnosis of head and neck cancer, and in particular also on for the identification for the study of novel devices to improve the early cancer diagnosis. This is a focal point. Early cancer diagnosis is a focal point to improve the chances of success of therapeutic interventions, because our aim is this, so the early cancer diagnosis, in order to try to promote new mass screening tests, both in Campania region and also in all the rest of the Italy. I think that this is the way that we can follow to try to get the best to this project. So the possibility to realize a test that can promote the mass screening of the population, to decongest, to accelerate the diagnostic processes that now is still long and exhausting. And now let's go into this section with the first speaker, who is Ilaria Rea. Ilaria Rea is a researcher at the Institute of Applied Science and Intelligent Systems of the National Research Council in Naples. And her presentation, the title of her presentation is Nanoparticles for in vitro and in vivo testing.
Okay, good afternoon to everybody, and thank you, Gabriella, for your introduction and also for this kind invitation. I'm a researcher of the National Research Council in Naples, and today I will be talking about our research activity on nanoparticles for biomedicine. Okay, a brief introduction to the concept of nanomedicine. That is the application of nanotechnologies to medicine. The aim of nanomedicine is to solve issues related to the standard medicine, such as, for example, the toxicity of drugs or the poor sensitivity of imaging techniques. Nanomedicine is a science developed in a research group characterized by several scientific expertise. For example, nanotechnology, material science, chemistry, engineering, medicine, biology. This because the group working in this field are characterized by multidisciplinarity. This is very, very important to develop nanosystems operating in the field of nanomedicine. The main components of nanomedicine are the nanoparticles. Nanoparticles for therapy, nanoparticles for imaging, for advanced imaging. Nanoparticles that can be polymeric, inorganic, lipid-based. And each one of these nanoparticles is characterized by different characteristics. For example, a low on high drug loading efficacy, or biocompatibility, biodegradability, a tunable surface chemistry modification. In our institute, we work with inorganic nanoparticles. This is because we have a long tradition on the study of inorganic matter. In particular, we realize gold and silver nanoparticles, silica and silicon nanoparticles, but also hybrid nanosystems constituted by gold, silica, and also polymer, in order to realize advanced nano devices with multifunctionalities. The main applications of these nanoparticles are, of course, advanced imaging, therapy, and multifunctionality. What are the main characteristics of inorganic nanoparticles? A tunable size and shape. A large specific surface area. For example, we realize nanostructured both silica and silicon nanoparticles, very useful for drug loading. A tunable surface chemistry, but also unique physical properties, optical, magnetic, electrical properties. In the field of therapy, I want to show a material that we are using from some years, a porous biosilica from diatoms. Diatoms are unicellular algae constituted by amorphous porous silica skeletons, including the organic matter, and there are several species of diatoms with different size and shape. It's very interesting that this skeleton is porous and also characterized by a nice specific surface area. The morphology of diatom surface is very similar to the morphology of synthetic structures that we realize in our laboratory. For example, porous silicon, nanostructured silicon, is a material obtained by electrochemical etching of crystalline silicon in a solution of based on hydrofluoridic acid. On the contrary, we have the comparison with the image, scanning electron microscopy image of a diatom. The morphology is very similar. Moreover, diatoms are constituted by a compatible silica, high surface area. They are characterized by tunable surface chemistry, very interesting optical and photonic properties, and the cost is low. And this is very interesting also for us. We work in particular with diatomite. Diatomite is the fossil form of diatoms, present in tons in our world, very cheap, and already approved by FDA for food and pharmaceutical production. We realize nanoparticles with a porous structure, with an irregular shape, and with the size of about 200 nanometers. Using a technological process based on mechanical crushing, filtration, and treatment in acid in order to remove the impurities coming from the environment, because diatomite coming from a mining industry. In these years, we have characterized the toxicity of our nanoparticles using several cancer cell lines, also exploring different surface chemical modification, for example, pegylation or the modification with the cell-penetrating peptides used in order to improve the cellular uptake of nanoparticles. And also we verified the hemocompatibility of our material, obtained very good results. In 2014, in collaboration with the University of Naples, we demonstrate the possibility to transport inside the cancer cell an sRNA immobilized on our nanoparticles by an electrostatical interaction using a positive peptide immobilized on the diatomite surface. In this confocal image, you can observe the presence of labeled sRNA in red. And we also verified the efficacy of this sRNA against the protein GAPDH that was downregulated by it. Then we also investigated the internalization and the localization of our nanoparticles modified with sRNA over the time in cancer cells using a label-free optical technique, so without the use of fluorochromes affected by photobleaching effects, imaging technique based on Raman. This in collaboration with the colleague Anna Chiara De Luca, and these are the results that we obtained. After 72 hours, our nanoparticles, label-free nanoparticles, were still clearly visible inside the cells. In collaboration with Dottoressa Claudia Tortiglione, for the first time we investigated the toxicity of diatomite nanoparticles, also with several surface chemical modifications in Hydra. Hydra is a little polyp, 2-3 millimeters long, that is a simple example of animal model. And the morphology of Hydra is very, very sensible to the toxicity of the environment. It can change a lot in a toxic environment, but in our case, under exposition to a high concentration of diatomite nanoparticles and also for a long time, the morphology of Hydra didn't change. The last year, in collaboration with the Department of Pharmacy of the University of Naples Federico II, we demonstrated the ability of our nanoparticles to transport a peptide nucleic acid inside cancer cells for cancer immunotherapy. PNA is a synthetic oligonucleotide that can inhibit the transcription of target genes. In this case, the PNA was covalently immobilized on the nanoparticles by a disulfide bond. After the internalization of functionalized nanoparticles inside cancer cells, the high concentration of the reducing agent glutathione induced the release of PNA of PNA. Here you can observe the characterization of the nanoparticles after each functionalization step, the drug release in presence or without the reducing agent, and also the confocal microscopy images. What can you observe? Observe that the presence of nanoparticles strongly improves the internalization of PNA inside the cells compared to the free PNA. And as a consequence, the downregulation of the PDL1 is strongly improved again. Multifunctionality. It's possible to join together different nanomaterials in order to have a nanosystem with different properties, different functionalities. In this study, for example, we realized a complex nanosystem with two aims. The first one, the release of galonisertib, a small molecule, inside the colorectal cancer cell. The second one is the simultaneous quantification of the drug released inside the cell. To do it, we realize a nanosystem constituted by a diatomite nanoparticle covered by gold nanoparticles, synthesized on it by a wet chemistry process. Then the drug, galonisertib, was loaded inside the pores of the diatomite nanoparticles, and finally all the nano complex was closed with a gelatin layer. Gelatin is a biopolymer, biocompatible. Also in this case we have a material FDA approved, and very important, it is pH sensitive. This because in alkaline condition, the gelatin layer is stable, but in acidic condition, the typical condition of a tumor microenvironment, the gelatin layer degrades, releasing the drug. Drug that has a very typical Raman trace, enhanced by the presence of gold nanoparticles on the surface of diatomite nanoparticles, gold nanoparticles acting as a SARS substrate. Our nanosystems is a SARS nanosensor that we used to investigate the release of the drug inside the cells. Release investigated by a completely label-free technique. In this image here, you can observe the SARS intensity of the drug over the time here, because The drug is inside the nanoparticles. The gelatin degrades in an acidic environment, releasing the drug. When the drug is close to the cell's substrate, its cell's signal is very high, but after the degradation of the gelatin, the drug is far from the cell's substrate, and its cell's signal decreases with its behavior, this behavior. From the therapeutic point of view, we observed that the drug, galunisertib, that we are releasing inside the cells, induced a transition from a metastatic state of the cells to a normal state. And this was verified, investigated the typical genes involved in this process, but also observing the change of cells morphology from an elongated morphology to a more rounded morphology typical of a normal state. And it was possible to compare the results of the morphology, the change of morphology over the time with the results obtained by SARS investigation, obtaining a perfect control of the dose and response of the cells. But it's possible to complicate again the nanosystems in order to have other functionalities. In this case, for example, we immobilized on our nanoparticle an anti-L1 CAM antibody in order to perform an active target, an active targeting of colorectal cancer cells, overexpressing the L1 CAM protein. And these nanoparticles were finally covered by using a gastro-resistant polymer for oral administration. To this aim, we used a microfluidic approach. And this is the drug release profile that we obtained. Without the gastro-resistant polymer, we can observe a very fast release in the stomach, but using the gastro-resistant polymer, the nanoparticles released the drug in the intestinal tract. And finally, it's possible to improve the biodegradability of our nanoparticles inducing a conversion from biosilica to biosilicon. This by using a technological process based on magnetothermic reduction. After this treatment, the nanoparticles are more biodegradable, but also they are characterized by a strong luminescence. This is very important because we can use this luminescence trace in order to observe the presence of nanoparticles inside the cells without using fluorochromes, because they can emit light alone. Okay, in conclusions, biosilica can be of diatoms can be an excellent and valid alternative to synthetic nanostructured silica, already approved by Food and Drug Administration, and also useful for realizing multifunctional nano devices for different purposes. Of course, several issues need further investigations, in particular the elimination routes and the biodistribution of these nanoparticles and other. Okay, let me thank the group working with me on these activities and you for your kind attention.
Thank you, Ilaria, for your very interesting presentation. Are there any questions from the audience?
Thank you, Ilaria. Very interesting presentation, interesting data. I'm not an expert on this kind of material, so my question is on the bioavailability of these materials and the things we want to use, for example, by intravenous injection is kind of nanoparticle. There is a lot of things possible and you are on the bioavailability.
Okay, thank you for your question. Forced biosilica from diatomite is characterized by a poor biodegradability, but it's possible to improve this parameter using a different strategy. One of these is the conversion from biosilicon to biosilicon. Because biosilicon is degraded into orthosilicic acid eliminated by urine. So in this case, it's possible to do this this strategy.
Also, question. Last presentation. I had some concerns about the people. There are some data about the biosafety of these particles. This is the first question. The second question is how to follow the signal in vitro in the animals and humans. It is possible to follow the signal and the localization of these silicon nanoparticles in vitro and how to do this.
Okay, thank you for your question. Allora, sorry, for the first one was on the safety of silica nanoparticles. Silica nanoparticles, synthetic silica nanoparticles, are already used in clinical trials. There are many investigations on these. Of course, further investigation, especially on the long effect of injection, are ongoing. For the biodistribution, it's possible, for example, use the property of converted biosilica to emit light. In the infrared region, for example, is simpler observed inside the tissues. Infrared, because yes, it's possible. In thin tissues, it's possible. Yes. Yeah. Not in my opinion, the fluorescence is not a good strategy in this case. Magnetic, maybe. It's possible also to conjugate silicon nanoparticles to magnetic nanoparticles, and then use a magnetic imaging. Thank you.
Are there any other questions? We could have a curiosity. If, from your knowledge, diatom nanoparticles have been used also for plasma delivery?
Diatomite nanoparticles, not. For Mirna delivery, not yet. We used them for sRNA, for PNA. It's possible yeah, it's possible, but at the moment, not yet.
Okay, thank you. Yes,
it's possible. Yes. The strategy is very similar. Yes.
If from literature there is already some evidence for this use, this kind of use.
No, but it's possible. It's possible.
Okay, thank you.
Thank you very much.
The second speaker that I have the pleasure to introduce is Dr. Marco Bocchetti. Marco is a brilliant postdoctoral researcher of our lab in Biogem of molecular biology and precision medicine, directed by Professor Michele Caraglia. Marco carried out a lot of experimental part of the project and take us into the heart of the project with his presentation titled Exosome Multiplexing Profiling, a Promising Strategy for Early Diagnosis of Laryngeal Cancer. Please, Marco.
So good afternoon, everybody, and thank you for the very kind presentation. So today I will talk about nanoparticle. It's not a surprise. So exosome multiplex profiling as a promising strategy for early diagnosis of laryngeal cancer. This is a timeline regarding the scientific interest about the exosome. As you can see, they were discovered around the 70s, but only in the last few decades the exosome are being seen as a potential diagnostic tools and also for personalized medicine. At this point of the day, you all are nanoparticle experts, so I will just keep on that and focus only on a few points which I need for the rest of the presentation. For example, the fact that the exosome can be found in the body fluids such as blood, urine, saliva, and they are important cargo of nucleic acid, lipids, and protein, both inside the nanomembranes and outside on the membrane. They can influence various physiological and pathological processes, and they are important for that even in the oncology. Their role in oncology is crucial, especially in the last few years. They can, it is proven that they can interfere with tumor growth, with angiogenesis, metastasis, and they are key regulator of cancers in general. Today, my focus will be on the laryngeal cancer, and which is also the focus of my research group in the last few years. And the diagnosis of this cancer is quite tricky because it's very, very difficult to get the diagnosis in the early stages due to the localization and the fact that the symptoms are not very apparent in the first place. A few data about the incidence worldwide. As you can see, Asia has the first position with 3.2 patients per 100,000 people. Africa is the last one, but Europe is in second place with 2.4 patients every 100,000 people. These are the data here in Italy, and as you can see, we have an high trend with 5 patients every 100,000 people, and the trend is increasing steadily year by year. So to account for that, we need to keep in mind the risk factors. And as you can see from this slide, smoking can increase the risk to develop this cancer by 10 times, while alcohol consumption by 4 times. On age and on gender, we can do much, but we know that men are more likely to develop the laryngeal cancer due to the inclination to the alcohol abuse. So you've seen that just acting on your habit, you can heavily reduce the onset of this cancer to appear. Also, HPV has a very crucial role in laryngeal cancer onset and prognosis. It's not in the guideline yet, as it happens as for pharynx cancer, but 67% of laryngeal cancer have a positive diagnosis for HPV. On the other hand, the laryngeal cancer, which are positive to HPV, but are easier to treat. They are better responders to the therapy. Now, just a few words before going back to the exosomes on liquid biopsy. Liquid biopsy is a kind of biopsy which allows, just with a simple blood withdrawal, to characterize genetically the cancer. So in the bloodstream, we know that cancer brings DNA from cancer and cell derived from cancer, which we can extract and analyze to get a complete genetic profiling of the cancer. And also it's very, very less invasive compared to the tissue operation. So we can do multiple times in order to get point by point the cancer information we require. And here we are to the smart test project. So this is a scheme of the project. As you can see, the final aim of this project was to functionalize a novel biosensor which can be applied in the clinical practice to diagnose the laryngeal cancer, especially in the early part of the onset. So this biosensor should work by recognizing the protein on the surface of the exosome, and in particular the exosome derived from cancer tissue. So the first part, the first thing to do was to discriminate which were the difference between cancer-derived exosomes and healthy-derived exosomes. So the first thing we do was extract the exosome, then functionalize them, and then we read the fluorescence by flow cytometry. I want to say that all this part was made here in Biogem, in which we had more than 100 patients treated. This is a bit of the protocol in details. We obtain the serum from patient with just centrifugation, and then we also recorded all the clinical information in order to build a biostatistics database to get further statistical analysis. To perform the extraction, the exosome extraction, we used a magnetic beads approach. We're using the CD63 as a capture mechanism. CD63 is one of the most widely expressed membrane epitope of the exosomes. Then we had to go through the characterization of these nanovesicles, and we did that by the use of a kit from Milteni, the MaxPlex exosome characterization kit, which contains a population of 39 different bits. Those bit population were differing by specific fluorescence, and also every single population could bind to a specific exosome epitope. So what we did was to incubate together the bits and the exosome, and so the exosome could be able to bind the specific bit population which were expressing the protein. At the end, we put a fluorescent antibody recognizing the exosome. So basically, we had like a sandwich with the exosome in the middle, so bits, exosome, and fluorescent antibody, which was then possible to read by flow cytometry. This is an overview of how flow cytometry works. Basically, the beads that we prepared in that way were suspended inside the fluid, and every single bead inside this fluid was make it pass through a laser, through different lasers. So the potential of the light scattering and also the emission of fluorescence give us all the information, both physical and non fluorescence, that those beads were bringing. And the output is like they are collocated inside the graph according to their specific properties as a single dots. Here you can see the final output of the instrument, and in the first graph you see the 39 different bit population. They are arranged themselves according to the different combination between green and blue fluorescence. Then in the graph below, we see the red fluorescence, which is exosome-specific fluorescence of 3 different samples. The naked beads, the blank, which we used with the plain water, and then the sample. As you can see, there is a clear shift in red fluorescence caused by the exosome, which were bound to the beads. So using this strategy, we could actually quantify how many exosomes were showing the specific epitopes. To do that, we had normalized several times because we had to try to reduce the bias induced by batch effect. So we had 4 normalization steps. The first one on the events of the word read. The second, we had to normalize on the event on single bits population. Then on blank negative control. In the end, we have some epitope control which we can use for normalization. And here we go to the final results. We found several membrane proteins which were overexpressed in patients, in exosome derived from laryngeal cancer patients. And the first one is CD14. CD14 is involved in chronic inflammation, which is a very common risk for cancer development. And also it is expressed on tumor-associated macrophages, which are able to infiltrate the tumor and promote tumor growth, metastatization, and also have a key role in immune evasion. For that, CD14 has a diagnostic and prognostic implication as a marker of poor prognosis. Then we found the CD20. CD20 is expressed on the surface of B-cell lymphoma cells and is also considered as a therapeutical target. There are monoclonal antibody targeting this specific membrane protein, the CD20, like rituximab, which acts with different methods to kill the cancer, which is expressing this protein. But I mean, this is not so easy as it seems, because cancer develop resistance very often to this kind of approach. This is interesting because this marker is also recently associated to solid tumor, for example, a few breast cancer and some gastric cancer. Today, we would like to give our contribution to characterize that in laryngeal cancer as well. Then we found CD44, which is associated with everything bad about the tumor. So tumor progression, migration, invasion, neoangiogenesis, and all these phenomena. It is also implicated in the maintenance of the cancer stem cells, which are a particular subpopulation of cancer cells, which are very resistant to chemo and radiotherapy, because they are in a quiescent state. So when the bulk population of the tumor is eradicated by the therapy, the cancer stem cells start to proliferate, causing very dangerous and very poor prognosis relapses. It's also involved in immune modulation and therapy resistance, and also again with DC14 as a clinical significance as a prognostic marker of poor prognosis. So taken together, all those three overexpressed epitopes in laryngeal cancer patients were used to functionalize the final biosensor. The final biosensor, which we said should be used to make a diagnosis just from a small amount of blood. The aim is to do that directly at the bed of the patient. So exploiting this knowledge plus the technological approaches by groups from CNR, we want to bring this device at the bed of the patients. So you've seen how these nanovesicles has the power to easily impact the cancer research. And just we need to keep in mind to always keep standardizing the protocol, both for isolation and characterization, in order to get consistent data which we can use in the clinical practice. So I would like to thank my group in Biogem, in the Precision Medical Lab in Naples, and the CNR. Thanks to Prof. Michele Caraglia and to you all for your kind attention.
Thank you, Marco. Are there any questions from the audience?
I have two questions. This question is how many CNR because you have built to the statistical difference between patients and healthy donors. The second question is, these are only three different antigens that we have found if we significantly, statistically significantly expressed in the serum patients.
Okay, thank you. But first question, we had around 40 reads from sera exosome derived from healthy patients, and we compared to over 60 reads from patients, laryngeal cancer patient exosome extracted. So this is more or less the numbers. And yes, we found several other epitopes which were overexpressed in laryngeal cancer patients. We were all related to immune escape, T-cell regulation, B-cell regulation, which more or less are going in the same direction of these three that we observe now. But these three were actually the best one to bring to a novel biosensor.
In ecology, we use largely rituximab for steroid-resistant hypothesis. Because of the rituximab also CD20, actually when you measure the expression is high, and if the population are not exposed to any kind of rituximab, also pretty easy.
Yes.
To target like podocytes. Specific cell express CD20 podocytes sa più tutto che
I guess it can be done. I mean, the technology is young. I mean, the application, as you already heard about the specialists in the field, is huge. The impact could be very important. So I guess also exploiting the exosomes, I guess we can also trying to see if we can direct something to specific place of the body. This is not a mature technology yet, but I guess on the paper it can be done. So basically, I think so.
Specific bloodstream that they have the highest percent size on the other side tested, and
of course,
and we have
the clinical trial. Yes, of course. Hi. Thanks.
So my question is towards genome. So you use the proteomic approach to identify the prognostic markers and then develop the chip. So is it possible to use the similar kind of approach to identify gene-based biomarkers, maybe using some genomics technology like the mechanism?
Yeah.
And what is your opinion?
I mean, exosome are cargos. So basically what we did now was just to indicate the surface in order to translate this technology to an early diagnosis device. But using the very same approach, we could isolate the exosome and get a full characterization of the inside. For example, the nucleic acids, but the protein inside, because protein inside are different from the outside. So we can actually, it's in the plan to continue on this field by characterizing the inside of the exosome at 360 degrees. So with all this possible omics application, yes. Of course, yeah. But we don't go then to check to functionalize the external, but we're gonna go to lyse it and then see what's inside. Yeah.
Marco,
hey.
Excuse me. What is the volume that you use to perform this exosome extraction? Volume of serum.
Yes, this was a tricky part of the beginning of the project, because we had to optimize the volume, and we assessed about 500 microliters of serum in order to proceed with the procedure. Yes.
Frozen or fresh serum?
We used frozen, so I guess also archive samples can be used in order to go with this procedure.
Sorry, Marco, and what is the indicative number of microvesicles of exosomes detected in volume?
This is a good question, actually, because we didn't get the precise number of vesicle, but we had to find a way to normalize before going to the characterization procedure. So we in-house built some protocol in order to quantify patient by patient by lysis. So we basically took a portion of the sample of a selected exosome and lysed it. So we quantified the protein, and then we go back to input to give the same input for the further part of the process.
Thank you.
Thank you.
So we can move on the last presentation, who is presented by Sara Martino. Sara is a second-year doctoral student for the PhD program in biochemical and biotechnological science at the University of Campania Luigi Vanvitelli under the supervision of Professor Michele Caraglia. The title of her presentation is Detection of Prognostic and Diagnostic Variants via nanostructured optical biosensor for early laryngeal cancer detection. Diagnosis.
Good afternoon to everybody, and thank you, Gabriella, for introducing me. And today I'm going to talk about detection of prognostic and diagnostic microRNA via nanostructural optical biosensor for laryngeal cancer diagnosis. I'm performing currently my research activity at the Institute of Intelligent Science and Applied Science and Intelligent Systems, and I'm supervised by Dr. Luca De Stefano and Dr. Ilaria Rea. And my PhD is in biochemical and biotechnological science at University of Vanvitelli, where my tutors are Professor Michele Caraglia and Gabriella Misso. So let's go to the main focus of this presentation. So the aim of the project is to fabricate a SERS optical biosensor. We will see later what a SERS optical biosensor means, for the detection of microRNA that appear to be biomarkers for laryngeal cancer. So what is laryngeal cancer? Laryngeal cancer is the most frequent head and neck cancer. It is characterized by a high mortality and high morbidity due to a late diagnosis. But recent studies have demonstrated that there are the presence of microRNA that appears to be as biomarker of this disease. MicroRNAs are short non-coding sequence that are involved in post-transcription modification and can control the expression of oncogene and oncosuppressor. And they are found, their peculiarities, that the fact that they are found at very low concentration. We refer to a range that is optomolar, femtomolar concentration. So they are really poor concentrated. So we want to fabricate a SERS optical biosensor. SERS stands for Surface Enhanced Raman Spectroscopy. Before to go into the details of what SERS is, I want to introduce what is Raman spectroscopy. Raman spectroscopy is an analytical technique where the scattered light is used to measure the vibrational energy modes of the molecules, and it can provide chemical and structural information if in fact it is possible to identify the so-called Raman fingerprint. But this technique has a huge limitation. It generates weak signal. So we need something that enhances the signal. So for this reason that we use SERS. So why we use SERS? Because we can use nanomaterials such as metal nanoparticles that are characterized by the localized surface plasmon resonance. Localized surface plasmon resonance are oscillation of the electrons density that create electromagnetic field. This electromagnetic field, when two nanoparticles, as I reported here in these examples, when they rearrange in close proximity to each other, these electromagnetic fields start to interact. And this gives the possibility to create the so-called hotspot. When the analyte resides in these hotspots, it is possible to have an enhancement of the Raman scattering. So the SERS signal is produced. So let's go to the biosensor fabrication. The proposed biosensor is made of electrospoon nanofiber that are used as a support. They are fabricated through the electrospinning technique of a polymeric solution of two polymers, caprolactam and caprolactam, which are referred to as CLO. Nanofibers are characterized by a high surface area platform, by a porous surface, which is fundamental for further functionalization. It is a biocompatible material and it is characterized by a high flexibility. The other component of this biosensor are gold nanoparticles that are in situ synthesized. And then I will give you then the details. So before the functionalization of electrospoon nanofiber, I want to show you in this slide the Fourier transform infrared spectrum of CLO nanofibers, because it is important to know how the material is made to understand which kind of functionalization strategy has to be used. Here on the right, I reported an image on how the electrospoon nanofibers appear before the functionalization. They are a paper-like material. In this spectra, we can see different peaks. The high intensity peaks are characterized by the one of the carbonyl vibrational modes of the carbon double bond between carbons and oxygen. And it is fundamental for this reason, because then we decide to use some strategies to functionalize the electrospoon nanofiber. In fact, we use a basic hydrolysis treatment and a temperature treatment to break down the peptide bonds and to have carboxylic group available. Then they will be activated using the ADC NHS chemistry, and then it was possible to pegylate the electrospoon nanofiber with the polyethyl glycol diamine, which is a molecule that presents two at both extremities amino groups that can bond so the available carboxyl group on the surface. Then we put the pegylated electrospoon nanofibers into a tetrachloric acid solution where the ion with gold ions were present. So then we decided to use both as a stabilizant and a reductant agent the decarboxylic acid terminated PEG. So this process was an overnight process. So the day after, we obtained this purple colored nanofiber, meaning that the functionalization with gold nanoparticles successfully occurred. So since we used the decarboxylic acid, we obtained gold nanoparticles that were whose surface was covered by carboxylic groups. And then it was possible then to immobilize the amino-terminal linear DNA probe that I'm going to show you in a bit. So before the experiment, I want to show the characterization of the electrospoon nanofiber functionalized with gold. Here it is reported an absorbance spectrum that shows a plasmon peak at 533 nanometers. Then we asked ourselves if this electrospoon nanofiber functionalized with gold could be a suitable CERS substrate. And to answer to this question, we decided to perform the enhancement factor calculation. The enhancement factor is a parameter that gives information about how a substrate is able to enhance the Raman signal for, of course, for CERS application. And the answer was yes, it is a suitable CERS substrate because we obtained an enhancement factors greater than 10 to the power of 6. Then in these slides, there are 4 different photos, images of electrospoon nanofiber functionalized with gold. And we decided to do this characterization to further confirm the functionalization with gold. As you can see in this picture, I don't know if you can see the arrows here, the electrospoon nanofiber are heterogeneously functionalized, and we are able to appreciate that gold nanoparticles create clusters. Maybe this is the reason why we obtain a great enhancement factor, because these clusters are useful for creating hotspots. So if we have a lot of hotspots, we can increment the CERS signal, the Raman signal, so to obtain a great CERS signal. Okay, let's switch to the experiment part. So I will show you the mobilization of the amino-terminal DNA probe, the hybridization experiment with a complementary target winner and non-complementary, and some passivation steps. So we immobilized the amino-terminal DNA probe, taking advantage of the carboxylic group that were available on the surface of gold nanoparticles, and we obtained a high signal. This one, the peaks, the red peak are the one related to the one that comes from the probe that is immobilized on the support. So we were satisfied by that because it was possible to see the different Raman fingerprint of the amino terminal DNA probe. For example, it was possible to see some peaks related to the phosphate here at 957 band position, or a peak at of the deoxyribose at 1454. And then, so that said, we decided to perform also the hybridization of the target Myrna, and taking advantage of the fact that we have an amino terminal probe whose sequence is complementary to our target. So we expected to see different peaks, mostly related to the RNA structure, so to the RNA Raman fingerprint, and we obtained in blue here, there are reported the peak related to this hybridization. There were good signals. In fact, the target Myrna shows specific Raman fingerprint that are here reported in this table in blue. For example, the of vibrational bondings related to the ribose, of course, that are a peculiarity of RNA. So, to further confirm the specificity of the signal, we decided also to use a non-complementary sequence. And what we obtained was that comparing the signal in red coming from the target and the probe with the compares to the non-complementary that should not be interacted with the probe, we obtained that the signal from the non-complementary were very low. So that was a good point. However, it's still possible to improve the signal discrimination. In fact, we decided to use for our future experiment a Raman reported labeled probe. Looking into the literature, in fact, it was possible to understand that there are plenty of strategies that we can use. For example, the one related to the molecular beacon probe, as here reported in this work. The molecular beacon is a oligonucleotide with a stem and a stem loop structure, which whose extremities can be functionalized differently. For example, in one extremity, it is possible to have a group, chemical group, with which we can immobilize on a plasmonic surface, for example, and on the other extremity we can add a Raman label, so a Raman reporter. So here I reported our future experiment, how they will look. So in the presence of the after the mobilization of the molecular beacon probe, we will see a great intensity of the probe signal, since we have a Raman reporter which has a specific Raman fingerprint, which is near the platform, the plasmonic support. So we will have a great signal. Once we use we incubate the Myrna target, this sequence will interact with the loop structure, so it will determine the opening of the molecular beacon, bringing further from the support the Raman reporter. And it will result in the low intensity of probe signal. So we will be able to better discriminate if we are interacting or not with a specific target. And of course, future experiment aims to calculate limit of detection using decreasing target concentration. So other experiments that we have performed are passivation of the surface using different type of molecules, like such as BSA, that we see that interacts with the electrostatic interaction with gold nanoparticles, or cysteamine mercaptoethanol, that thanks to the bonding that is created between the thiol group and the gold. And we so basically demonstrated the high degree of functionalization of this approach. So I'm glad to show you this slide, because finally the gold nanoparticles immobilized on the Clark law nanofibers biosensor has been patented on April 2023. Here in this slide, there is the title of the patent. There are the authors, that most of them are present here today. And last but not least, I want to show you this application that we are developing for the detection of head and neck squamous carcinoma exosomal antigen. So basically, we use the same biosensor platform, so nanofiber functionalized with gold nanoparticles, but we will use two different recognition elements. And for this reason, it is called the sandwich strategy, but I would say an hybrid sandwich strategy, because we will use an aptamer, which is immobilized on gold, that specifically recognize the exosome, the exosome of interest, and a CERS nanoprobe, which consists in a metallic nanoparticles labeled with the Raman reporter and functionalized with the antibody that are specific to the antigens that, as Dr. Marco Bocchetti before explained, are overexpressed in this cancer, like the CD14, CD20, and CD44. So, in conclusion, the take-home message are that this biosensor is, has shown to be a suitable sense substrate. We observed high signal from CERS signal from DNA probe and target. Future experiment aims to better discriminate the signal using a Raman reported labeled probe. It has shown to have a high degree of functionalization. We obtain an approved patent, and this sensor can be also used for application for the detection of cancer exosomal antigens. Thank you for your attention. I want to thank my group, Nanobiosystem group at ISASI CNR. I want to thank also the Precision Medicine Lab, and of course I want to thank Biogem to give me the opportunity to be here today.
Thank you, Sara, for your valuable presentation, and congratulations for your huge work. And then any question from the audience?
Do you think that there is possibility to use another support, such as masking?
Of course, it is possible, not related to nanofibers. There are plenty of nanostructure, plasmonic nanostructure that can be used, that maybe can also have a high ability to enhance the Raman signal, so to achieve rate enhancement factor, of course. Which are the alternative strategies, you mean? Yeah. Of course, it is possible to have another strategy that can be in mushrooms, but they require other type of fabrication steps. We require a specific lab to do it, the clean room, and but of course it is possible. I like nanotechnology because it seems that everything could be possible, and most of the time it is. So, yeah, I hope so. For a colorimetric assay, I would say that a colorimetric assay would give you something that is not quantitative but qualitative. I mean that for this kind of detection, like Mirnas, that are really poor concentrated, I prefer to use like a quantitative strategies that can be, for example, the one that I've shown here with molecular beacon, but also for a fluorescence application, not only with CERS. Okay.
And are there any advantages in detecting the exosome compared to Biogem detection?
Yeah, of course, I think there are, because the main problems with Mirnas is the fact that they are present at very low concentration in body fluids, so it is difficult to detect them. So having, for example, exosomes that are basically they are vesicles that are compared to nanoparticle inside. So having this area to surface volume, which is better, they can host a lot of antigens, so it increased the possibility to interact with the antigen and so to detect them actually.
Thank you. Sara, excuse me, the functionalization of this sensor can be performed with only one aptamer, for example, or multiple aptamers?
No, you mean different kinds of aptamers, so to have a multiplexing detection, for example. Yeah, I think it can be possible. Of course, it is important to take into account what we are looking for, because the biosensor that I reported as another recognition element that are the metallic nanoparticles with the Raman reporter. So I would say that it's also important to use also another CERS nanoprobe with another Raman reporter to better discriminate from the other that we are looking for.
Okay. Any other questions? No? No? We thank all the speakers of this second section. We invite Michele Caraglia for closing remarks of this meeting.
I want to thank you all for participating in this meeting, and I hope that this could be also a chance to reinforce our cooperation in several fields in the search for therapy and for the diagnosis of this kind of tumors. Thank you again for you all, and we will see very soon. Okay, thank you.